and I slightly changed the topic, but not the contents. I simply changed the topic. The contents are exactly what I advertised, and I'm going to talk about uncertainty quantification, which is a very important problem in computational engineering and science these days, and in the context of a particular class of, but albeit very important class of PDEs, which are nonlinear systems of conservation laws. Now, this is not supposed to be a sort of a colloquium or a presentation in a lecture. Rather, this is supposed to be an instructional school, right? So, I'll try to be slow, and I would appreciate if there is some interaction with all of you are graduate students, there is some interaction with all of you. So, please ask me questions. At some point, I'll use the blackboard. Majority of my presentation is on the slides, but at some point I switch to the blackboard for technically more involved things. So please do stop me, ask me questions. And the way I organize it is that I have 3 modules, roughly 1 hour each, roughly. And at the end of each module, I'll take a short break, like 15 minutes, and then we resume. Okay, so let's see. So I start my presentation by showing you a beautiful picture. Rather than talk about some equations. So this is a picture which comes from a place called Lituya Bay in Alaska. As you can see, it's a black and white grayscale picture. This is a rather rugged, nondescript wild landscape. It's a beautiful bay, and why do we care about that? It's clearly uninhabited. The reason why we care about it is because what happened here on the 9th of May 1958 was truly momentous. So first of all, this is in Alaska, so there are a lot of earthquakes in this area because it's along what is called the Fairweather Fault. This is a big earthquake, 7.8 on the Richter scale. Because of that, what happened is that because of the earthquake, a part of the mountainside essentially collapsed onto the bay. And when it collapsed, what happened is that there was a rock slide, right? And this is 30 million cubic meters of rock. So you can imagine the amount of rock that was there to have 30 million cubic meters of rock. And all this fell onto the bay here. This is a rather shallow bay. And because of that, it triggered a tsunami. And not just any tsunami. It's a tsunami which is the maximum wave height ever recorded, 100 meters. So you can imagine, you stand here and you have a 100-meter wave. And this is exactly what happened here. And there was, and why do we know about this? This is because this is a picture taken after the tsunami, I think a few days after the tsunami. And you can see that up here, the entire mountainside is flattened, right? All the trees here are flattened all the way up to about 525 meters, 1724 feet. A lot of run up here, but this was truly a gigantic, a momentous tsunami. And in tsunami simulation, in the business of tsunami simulation, it's considered quite challenging. It's a benchmark test problem, considered quite challenging to be able to simulate this tsunami. How can we do this? How can we simulate a tsunami which has a 100-meter wave height, right? So what's the process? All of you are students of computational science. This really is a question in computational science. So first, what is needed is a mathematical model, right? And thankfully for this particular problem, there is a suitable mathematical model. It's called the Sava-Hutter shallow water model. Sava and Hutter were 2 Swiss geophysicists who worked on rock slides and avalanches, and it's named after them. The idea is that you have 2 phases. So if you look at it, you have rock, right? Rock is also granular material, it flows down, and then you have water. I'm not going into the details of the model. All that I'm going to show you is what happens to the model in 1 space dimensions. So this, for instance, the height of the water. This, for instance, is the height of the rock. These are momenta, and there's a lot of stuff here, a lot of momentum exchange going on. And there are a bunch of parameters here, bottom topography, friction terms, and so on. So there is a mathematical model, and this mathematical model is based on what is called a non-conservative hyperbolic system. And Sebastian here has worked quite a lot on that, many other people also. And what it turns out that there are pretty good numerical methods to handle these systems. For instance, what are called path conservative finite volume schemes. People in Malaga, some of my colleagues, they have done this optimally on a GPU. So you can even implement this. And then finally, so you have a numerical method, you have a mathematical model, and finally you need parameters, right? Because there are lots of inputs to this model. You need initial conditions, you need boundary conditions, and you need all these parameters here, which I have put in, at least some of them in color. So you have initial data, boundary conditions, acceleration due to gravity, we all know what that is. The density, ratio of the densities of the two materials, bottom friction, Coulomb friction, interlayer friction. Once you go into the details, there are quite a few parameters. So these are the three things that are needed. You have a mathematical model, you have a numerical method, you have parameters. And if you put all the three things together, then you can do the simulation, and in this case you can do it rather successfully. So here is the simulation which was done by some people in Malaga several years back. So this is the rock falling down, this is just a still photograph, rock falling down after 39 seconds of the event starting, and then this generates the waves, the tsunami waves, and as you can see there is here this the big wave that runs up this shore, and this is 100-meter high. So indeed we are able to simulate this kind of a very complex and let's say extreme event. But in the next slide I am going to say that this simulation has to be understood a little bit more critically. It looks very impressive, right? And if I show you the movie, it's really a sort of an impressive simulation. But let's try to analyze it a little bit critically. So let's try to think about what are the sources of error in this particular simulation, right? So the first source of error is of course modeling error. After all, there is physical reality, there is a mathematical model. How well does the mathematical model conform with the physical reality? So that's your modeling error. So it turns out that the Sava-Hutter model is rather a good model. People have done a lot of experiments in the lab and they found this to be a good model, a good fit, also for physical reasons. Then what about the discretization error? After all, it's not like we are solving the Sava-Hutter equations exactly. We are solving them with a numerical approximation. And once you have a numerical approximation, you have some discretization, both temporal as well as spatial error. It turns out that in this particular context, this is a good numerical method, the one that is used for the simulation. The discretization error can be made as small as possible by simply taking a more refined mesh. The third set of errors, so remember we have a model, we have a numerical method, but we also have parameters, and there are a bunch of parameters, right? There are all these parameters. Several of these parameters can be measured rather accurately. However, there are three parameters here. So this is this R, which is the ratio of the densities. Then we have this Coulomb friction and this interlayer friction. You have to make these measurements. So you go to the lab, you take the material and you start measuring. And when you make these measurements, this is not very reliable. So people have done these experiments in the lab and they discovered that you have unacceptably high errors for these parameters. What does that mean? So if you do experiments, you measure something once, you measure something twice, you measure something 10 times or 100 times, whatever you can afford, and then you try to find out what is the standard deviation, for instance, compared to the mean. And it turns out the standard deviation is like almost 100% of the mean. So in these measurements are useless because the noise to signal ratio, which tells you how sensitive the measurement is sort of unacceptably high. It is so high that it's useless. So this simulation could very well be useless because by changing the parameters slightly, because we can never make these measurements precisely, by changing the parameters slightly, you might get a completely different answer. And this is sort of the crux of, so as I say, high measurement error implies very low trust in your simulations. And this is a, I would advocate, is a generic situation in science and engineering that whenever we have to make simulations, we have tons of inputs like coefficients, parameters, initial and boundary data. These have to be obtained by measurements. These measurements are uncertain. You have some probabilistic model of these. And because the inputs to your problem, inputs to your simulation are going to be uncertain, it's sort of clear that the output, the solution itself is going to be uncertain. And there are some other uncertainties that will crop in, you'll say that. And this entire study of these uncertainties, or at least part of it, is what we call as uncertainty quantification. So at least for the purposes of this talk, it means first of all, we have to accept that the inputs to your model are uncertain. Also the dynamics as a result is uncertain. So we have to model these inputs in a probabilistic manner. Then once there is a input uncertainty, there will also be an output uncertainty, solution uncertainty. This has to be computed efficiently. And finally, you have to interpret or, for instance, make a risk assessment. There are some backstream down-end processes that are there. So all these three things are covered under what is called uncertainty quantification, or rather I would say in these days it's called uncertainty propagation. So the idea is you have input uncertainties, you will obtain output uncertainties. How are we going to compute this, right? So this is the basic question. So instead of having a simulation like this, which is just one simulation, can be very uncertain, and things can be completely different if you have a slightly different parameter choice, what the end of this process will be something like this. Instead of a single simulation, I'll provide you with the mean, and you see the mean is, this is over several hundred simulations, thousands of simulations. I'll describe what method is used for that. Now you see in the mean also we have very big waves here as well as here, but this is not the important quantity. The important quantity is the variance. So the variance tells you how sensitive the whole simulation is, right? So as you can see, the variance here it's large, but here remember that the big wave was out here, the 100-meter wave. Here the variance is rather small, it's like 5. So the standard deviation, or about 10, the standard deviation is about 2 or 3. So as the noise to signal ratio for the output is only 2%. For the input was more than 50%. So somehow the uncertainty, there's a nonlinear problem. Just because you have uncertainty in the input, the output uncertainty could be small or large. It depends, right? So here, something like this tells you that I can trust this simulation much more, because okay, this is with very low variance, with high certainty, we can say that there were large waves. So it is not a result of some fluke. This is later in time, so this is at 120 seconds after the event. So this is the mean, and this is the variance. You see rather low variance. So this is a problem where uncertainty, even though large in the input, is small in the solution. It could be very different in other problems, and you will see examples of that in a bit. So what I am going to do in this lecture series or this course is I will talk about uncertainty propagation, which is a particular part of uncertainty quantification, but instead of looking at sort of arbitrary PDEs, which is too much, what I am going to focus is on PDEs that I specialize on, which are hyperbolic systems of conservation laws. Okay, so any questions so far? Or am I being too fast? Or please feel free to ask me questions. No? Yes. Yes. Yeah.
Something like uncertain dynamics or something like this.
Yes. This is.
In models.
Yeah, uncertain dynamics. The reason why I put it is because you'll see that in about 45 minutes. What does uncertain dynamics means? So at the moment, think in, for instance, here the dynamics. So uncertain dynamics means that even though you have very low input uncertainty, the dynamics is such that you have an increase in uncertainty. So it's sort of dual of this case, right? Because here you had very high input uncertainty but very low output uncertainty. So you're just lucky. Means there is a nonlinear problem, it can go either way. Okay, so let's try to focus on what PDEs I'm going to concentrate on for this lecture series. Some of you probably know very well, probably Sebastian teaches it, so we'll see. So conservation laws. So this is a cartoon describing what a conservation law is. So you have a domain and you have a quantity of interest. This could be temperature, pressure, velocity, concentration, whatever you can think of. And then the idea is very simple. You take any subdomain of this domain, so this is an example of that. The rate of change of the average quantity, somehow you are interested in the average quantity of interest. The rate of change of this is given in terms of the fluxes, right? So rate of change of any quantity is given by, in the absence of sources, is given by how much of stuff comes in, how much of stuff goes out. So this is exemplified by the fluxes here, which are acting at the boundary. Now you can use the Gauss divergence theorem and you get a system of conservation laws, which says the rate of change of a certain quantity is balanced by the fluxes through its boundary. So this is a conservation law. And quite a few models in physics follow this. The prototypical example, the one that I'll focus on quite a bit, are the equations of compressible fluid flow, right? So compressible fluid flow, the Euler equations. So you have conservation of mass, so rho is the density, U is the velocity field, so this is the continuity equation, it tells that the mass is conserved. Then you have momentum, so you have momentum is a product of mass and velocity, and conservation of momentum says, so momentum is conserved along the advective direction, and Newton's law tells you that the force that is acting on the fluid is given by the gradient of pressure, which is this term here. And finally you have the conservation of energy. So energy, for instance, for an ideal gas will be the sum of the kinetic energy, which is out here. So this should have been an absolute value. So this is the mass times velocity squared, and then you have the internal energy, which for an ideal gas is given by this. Gamma is the gas constant, P is the pressure, and this is the conservation of energy. So when you stack these three things together, we get a system of conservation laws. The capital U, remember that I always had a capital U here. For this particular case is rho, the density, rho U, the momenta, E, the total energy, the flux is given over here. So this is 4 components if you're in 2D and 5 in 3D, right? Because velocity has the same number of components as the dimension. So this is a prototypical example of systems of conservation laws, but there are plenty of other examples. So you have shallow water equations, which comes from oceanography or meteorology. Then you have the magnetohydrodynamic equations, which come from plasma physics. In all reservoirs, you have Buckley-Leverett equations, Einstein equations. Many problems can be fit into this framework, right? So this is sort of a good class of equations to look at. And the point is that even though this looks like a very large class of equations, there are some common features. So one key common feature for these equations is hyperbolicity. That's why I said hyperbolic systems of conservation laws. So what is hyperbolicity? So remember that we have the flux function here. So this is expressed by certain conditions on the Jacobian of the flux function. And just in a sort of a brief way, what hyperbolicity tells you is that the solutions of these equations, the equations that I wrote down, these are waves. They have the structure of waves, and these waves, they move at a finite speed. So this is sort of finite speed of propagation is hyperbolicity. Another common feature which is important for these equations is the role of the non-linearity. So even the simplest example of these equations, so the simplest example of these equations would be the Burgers equation. Perhaps we can write it down. So we take, so you have ut, u is just a scalar, and u squared over 2 x equal to 0. So this is the simplest example, right? So this is one scalar quantity. This is the flux, which is quadratic. So the simplest example of a non-linearity. And even for this equation, I think all of you should know this. You have the formation of shock waves, right? So if you start with initial data, which is smooth like this, in a finite time, which in this case you can predict, you have this wave steepening out, right? And because of that, you have the formation of discontinuities. So even for very sort of smooth data, you will always have discontinuities. So here non-linearity, it takes a problem which has, let's say, small derivatives, and it makes the derivatives larger. So that's why you have formation of shock waves. Because you have shock waves, you cannot have classical or smooth solutions of these equations. You have to interpret these equations, taking into account the discontinuities, and this is done by what is called as weak solutions. Okay, I need to explain a little bit the background behind these equations in order to even start with uncertainty quantification. So you take a test function. The equations are in the conservation form, so you can always, by the way, I should write down the equations, otherwise I need them all the time. So you have vector. So this is the simplest example, but you have a vector, you have the divergence operator. So this is the equation that is the main equation that we are looking at, right, with several examples. Now for this, you can see that this is in the divergence form. So we can multiply with the test function, integrate by parts, and when we do that, you get an equation or an identity like this, and we demand that this identity holds for all test functions. It's a little bit like a variational form for finite elements, right? But as soon as you work with these kind of weak solutions, they are never unique for nonlinear problems. So you need some additional admissibility criteria or entropy conditions, and these are inspired from the second law of thermodynamics. So what essentially they mean is that in addition to this equation, you have to obey another inequality, not equality, inequality, because the entropy, the mathematical entropy decreases, the physical entropy increases. So you have to obey another admissibility condition to have any chance of uniqueness. So this is sort of the basic framework here. So you have to look at weak solutions because you have discontinuities, and you have to put some additional conditions in order to enforce uniqueness, right? And probably most of you know this, but I'll just give you a very short crash course on what sort of numerical methods do we have for these equations without uncertainty, because in order to deal with uncertainty, we have to deal with the case where there's no uncertainty first. Right, the simplest method is what are called finite volume schemes, right? And finite volume schemes are very natural because the original equation itself was in a finite volume form, which said that the rate of change of a certain quantity of interest is balanced by fluxes. And this is what is reflected here in one space dimension. So you have a grid, right? So this is space out here, up here is time, and you have a grid. So uj is the quantity of interest, which is a cell average. Makes sense to consider cell averages, right? Remember that the functions are discontinuous. So if you consider a point value, it need not even be well defined. So you need a cell average, which is given here. And then all that it says is the rate of change of the cell average along this cell is given in terms of the fluxes, which tell you how much of stuff comes in or goes out here, how much of stuff comes in and goes out here. So it's a very intuitive way of thinking about it. And then you have a formula which comes like this. And the way to define these fluxes, there is a whole theory. Sebastian probably teaches this in his classes here. And this is based on Riemann solvers. So you have what is called a Riemann problem at each interface. You have.
I should say also in the engineering, in the aerodynamics, they teach us so many students here.
Yes, probably.
Also in civil engineering.
Yes. So this is sort of, many people, you guys should know this, but I just, so there are different kinds of approximations to solve this. The point about these approximations is since somehow your basis function, so this is the formula, but since your basis function is just piecewise constants, you have at best a first order accurate method, right? Because piecewise constants can approximate a function, a smooth function to first order. So to get high order, you have to replace piecewise constants with high order basis functions. For instance, piecewise linears, right? So instead of having piecewise constant functions, you have piecewise linear functions. So to define the fluxes, instead of looking at the constant values, you take the value out here on the edge of the cell and you define the same formula. You have the same flux formula, but you replace the inputs to it in terms of the piecewise linear approximations. Sounds very easy. However, there is a slight complexity here because of the discontinuity. If you do it in a naive manner, for instance, even for the linear advection equation, so linear problem, if you take a discontinuous data, it just moves, right? And then even if you take a good flux, upwind flux, if you take, because this slope here is approximation of the derivative of the underlying function. And you know that the derivative is or the function itself is discontinuous, so there are two derivatives, right, in a way. So what should you take? If you take the wrong one, then you get oscillations. And so there is a whole theory about how to do this. So you don't want this kind of spurious oscillations. So one way to do this is to look at the total variation, and total variation tells you how much of oscillations are there. You have to reduce it or you have to eliminate it. So one way is what are called limiters, slope limiters. So you just choose the slope intelligently. And if you do that, then you get non-oscillatory resolution. So here's an example. So this is what is called the short shock tube for the one-dimensional Euler equations. So the density is out here. The exact solution is in, or a high resolution numerical solution is in pink or magenta. And this is the density, the velocity, and the pressure. The first order scheme was, at least for the density, it's in green. You can see that it's dissipative, particularly after what is called a contact discontinuity. With this second order non-oscillatory methods, you get a much better resolution of the discontinuity. So you get this to be very small, right? And the same with the density and the pressure. So there is and you can do even high order methods, because why do you stop at second order piecewise constant functions? Why not use piecewise parabolic, piecewise cubic, and so on functions? You can do that. There's a whole huge literature on different kinds of methods, ENO, VNO, DG. For time integration, one uses what are called strong stability preserving Runge-Kutta methods. Again, you have many people here, Sebastian, Sigi Muller, Kjorgmai, who teach these things, so I am not going to focus on that. And here's an example where you need high order schemes, right? So this is again for the Euler equations in one space dimension, the exact solution. So you have some waves here, you have a big shock sitting here, you have a sequence of weak shocks sitting here, and you have a lot of high frequency smooth oscillations. So these are real oscillations here. If you take a second order scheme, this is in blue dots, so you lose these oscillations entirely. and if you take a fifth order Wiener scheme, then you start getting them back. So sometimes you need very high order schemes. But the bottom line is that there are good numerical methods available, provided that you look at the deterministic problems. So if you know the uncertainties, or there are no uncertainties in the system, then there are good numerical methods available. For instance, you can do things like, in my group, we can do core collapse of supernovas. This is with the magnetohydrodynamic equations, so very complicated fields, magnetic field and so on. You can do things like waves in the solar atmosphere. So you can see that this kind of spiral waves, this is again with the magnetohydrodynamic equations in 3D. The classical examples are flows past aircraft or aerofoils. So here's an example. This is DG with a space-time adaptive grid. So you see the space adaptation. This is a supersonic flow. So you can see how the flow looks like. You can do tsunamis. This is a classic example. This is a tsunami generated in the Mediterranean. Shallow water equations. So you can see how the tsunami moves. This is at 2 hours, at 4 hours. So you can do a lot of cool stuff. Okay, so this is, many people think that this is a mature subject. We will see whether that is true or not. But as I said, our point was not to do this. So we know that for the underlying problem, so here's the PDE. For the underlying PDE, we have weak solutions, or rather entropy solutions. We have finite volume methods with a lot of technology behind them. But the issue is uncertainties, right? So we have uncertainties in all possible places, uncertainties in the initial conditions. For instance, in this problem, the initial conditions are not known exactly, because there is an earthquake. The earthquake will happen somewhere around Crete, and then from the earthquake there is a model on how to determine the initial wave height, and this is full of uncertainties. There could be boundary conditions which are uncertain, flows past an aircraft. You don't know exactly what the Mach number is going to be, you don't know exactly what the angle of attack is going to be. There are always small uncertainties in that. And there are a bunch of uncertainties in source terms, in the coefficients. This is what I showed you before in the tsunami in the rock slides. And the point is, given this uncertainty in the inputs, we have to construct uncertainty in the solution. Given that we know that underlying this, we have entropy solutions, and underlying this, we have some good finite volume methods, right? So this is sort of the baseline. And how do we do that? Again, so this is a good place to ask some questions if you have any. Feel free, don't be shy. Means you can, if you don't understand something, you can always ask. No? Yes, yes, good.
Is it also important to think about how the actual real system responds in case some inputs are tweaked slightly?
This is what you have to, how do you know that, right? Means this is the whole point of uncertainty quantification, is to compute these changes. So you have to be precise in what do you mean by tweaked slightly is, and you have to be precise in what do you mean the response is going to be. And this is exactly what I am going to describe in a systematic manner. So you'll see that in some cases slight tweaks are going to lead to large changes. In some cases they are not going to lead to large changes. You cannot just write down a formula to do that. That's somehow the essential point. Do all of you know what finite volume methods are? Maybe a show of hands. So how many of you have seen a finite volume method? Okay, everyone. So that was a bit redundant. No, you guys don't qualify, right? How many of you know DG, for instance? DG? Okay, so you don't qualify, Hokon. Okay, but it's a finite element method. We don't, finite volume is what we stick to. So what are the issues? So now exactly coming to your question, right? What does it mean to tweak slightly? Now we have to be precise, we have to be quantitative. So the question is, how do we model uncertainty in the inputs? And then how do we model uncertainty in the outputs? So you need some sort of a mathematical framework for uncertain solutions. And of course, underlying everything is efficient numerical methods for UQ. And you'll see in a bit why we need efficient numerical methods for UQ. So there are many ways to model input and output uncertainty. The most common way, and the one that I'm sticking to here, will be a probabilistic framework. So I'll try to simplify this quite a bit. Means we can do it very mathematically, but I'm not going to do that. But I have to introduce some basic setup here, right? So we will use the standard probability space framework, which goes back to Kolmogorov 80 years ago, I guess. So we need omega, which is a set of outcomes, sigma, which is all possible events, what we call as a sigma algebra, and we need a probability measure. So probability measure is just a mapping from omega to 0, 1, and the total mass is going to be 1. So these things are necessary. Just imagine that you have coin tosses. So in a coin toss, the two events are head, or a single coin toss, it's head or tail. The sigma here is a null set, head, tail, and probability tells you half and half, right? Or this is essentially the thinking behind it. But now it's not enough, because remember that I have, for instance, let's simplify life a little bit, otherwise this becomes a tad complicated. So let's say that we are interested, all our uncertainty is in the initial conditions. It's similar treatment for other things. All our uncertainty is in the initial conditions. So we have u naught of x, and this object here, which is a function, is uncertain. Okay? So because it's a function which is uncertain, the way to model this uncertainty is using what are called random fields. Okay? So what are random fields? So in fact we will use random fields to model initial data, boundary data, fluxes, sources, all of this can be done. So at the bottom line of this slide is the following, that you have a probability space, remember, so you have omega, sigma, these objects here. So what do you do with the probability space? What you do from the probability space is that you toss coins or use a random number generator and you extract something out of it. So each realization of this probability space is going to be a function. That's what a random field is. It's a mapping between the probability space, and f here is just functions. It could be integrable functions, square integrable functions, bounded functions, and so on, right? So this mapping here has to be measurable, so you should be able to integrate things, and this is what a random field is. So for the purposes of this talk, think that each time you make a draw from this omega, you get a function, okay? And there is a nice relationship between this omega and the function that you get. For instance, I take the Burgers equation and I am interested in the initial data being uncertain. So each time I make a draw, which is mapping here, I get a draw. This guy here is going to be a function which is bounded, okay, and which is also going to be the bounded variation. It's in bounded variation, so it has controlled oscillations. So this is what a random field is. It's sort of a complicated way to express a very simple thing, which is each time I make a draw, I get a function. Because what you are used to is each time I make a draw, I get a random variable. You go to MATLAB, say rand, then it gives you a number, right? But you say rand 100, you get a vector of size 100. Now just imagine that you generalize that, and each time you say rand, you get a function, and that is what is a random field. Okay, so it's a simple object. Once you have a random field, yes.
Maybe I missed that, but the last.
Almost surely, yeah. This. Almost surely. Sorry, but this I don't know if everyone is from math background. I have not changed my slides. This is, but almost surely means whenever you draw from some probability space, sets of measure 0 don't matter, right? You don't care about them. So it's almost surely. Sorry. But let's try to make this concrete. What does it mean that each time I make a draw, I get a function, right? Well, let's try to make this concrete, and this is important in what we are going to do, because a function is an infinite dimensional object. To be able to compute it, you need to make approximations anyway. So one thing that you can do is, so we represent these random fields. One way to represent them is through parameters, parametric representation. Let me give an example. So this is a very classic problem, right? It's a shock tube. So I think it's in Stuttgart that they have the big shock tube. They have these experimental facilities in Stuttgart. I always thought that they had it in Aachen, but I think it's in Stuttgart. So you have this big shock tube. So you have a cylindrical tube, and in the middle of the tube you have a diaphragm. You have something which separates two phases. Do you guys have it here? No. You have it here. This is a
20 meters long.
Yes, 20 meters long. You know, there's a big three-dimensional object, and you have a diaphragm, and you have a pump which extracts air out from one side, and the other side is normal air, and then you release the diaphragm, and you see how the flow evolves. This is a shock tube, right? So now when you take a one-dimensional cut, this is what you would get initially. Initially what you get is, I draw a picture because I didn't have it. Initially what you would get is some object like this. So this is the density in the left, the density in the right, then you have the velocity is 0 in both sides, so this is your velocity because there is no flow in the beginning, and something with the pressure also. So pressure could be something like this. So this is your PR, PL and PR. It's just an example. So it could be something like this. But now comes the point, right? So this shock tube is an experimental facility and you have to make measurements. So now the exact location of this, engineering is always imprecise. You are never going to say that this is exactly at the point 0. Maybe there are some slight tweaks, as someone mentioned. Maybe it's not at 0, maybe there is a little bit of variation there. And this is exactly what it says, there is a little bit of variation there. So this variation is measured by a random variable, random number. So you make a choice and you say that this is between minus 0.2 and 0.2. This one was a bit large, but it could be minus 0.02 and 0.02. So, and it's uniformly distributed. So there is some engineering imprecision. And now you're making a measurement, right? So you're saying that rho L and rho R, or PL and PR, I have to measure these things. Maybe they are not known exactly. Maybe there is a slight error in them, right? And for instance, so here you have another random variable which sort of expresses how much of this initial uncertainty is there. So the entire uncertainty, even though these are functions, I've expressed them in this simple way by two uniformly distributed random parameters, which says that there is uncertainty in the initial location and there is uncertainty in the initial amplitude. And you can represent this by this kind of a diagram, which tells you the blue is the mean, right? So when you do means, since you have uncertain location, you have this sort of a smoothing here, and mean plus standard deviation and mean minus standard deviation. In engineering, these are what are called error bars. So they tell you how much of sensitivity is there. There is a little bit of roughness here, right? So there is a little bit of tweak, as someone described. So this is one way to describe random fields in terms of a few random parameters which have some physical basis. Here's another example which is very common. This is difficult to do experimentally, but it's a very common test case. It is the interaction between a bubble and a shock wave. For instance, it's very common in astrophysics. So you have a high density bubble here and you have a shock wave here. So this is in the density, and this shock wave is supposed to hit the high density bubble and create a lot of interesting dynamics. But again, to do this experimentally, or these kind of things are common in astrophysics, to observe them, you're never going to do it exactly. For instance, how do we know that this shock is sitting exactly at this location? There is probably some uncertainty in that. How do we know that this is exactly the value to the left and value to the right of the shock? Maybe there is some slight uncertainty in that. Who tells us that the bubble is exactly a sphere? Nothing can be exactly a sphere, right? So there could be some changes in the geometry. Similarly, the value of the bubble, the value of the density, this is between 10 and 1, means why should it be 10? Why not 10.05 or 9.95? So all these factors you can do in terms of 11 parameters. So this is the density, the bubble density, the shape, and so on. And you can see here, the mean is slightly distorted sphere or circle in this particular case. There is some uncertainty here which is seen in the variance. So shock location, amplitude, bubble location, amplitude, and geometry. So you have 11 parameters. So even though each realization from this, each time you make a draw, you have 11 parameters which leads to a function, but still it's completely described in terms of 11 parameters. And this is very common. So each time you do this in engineering, you know what are your sources of uncertainty and you assign a certain model to this. In this case, it's uniformly distributed. It could have been normally distributed. Let's do this a little bit more complicated way. So here, for instance, is what is called a digital terrain model. I don't know if they do it in Germany, but in Switzerland, where I live, the whole of Switzerland, there is a digital terrain model. What does it mean? Digital terrain model tells you, given a certain point in Switzerland, what is the height of that point, okay? And the next point, what is the height of that point? How do they do that? They actually have helicopters and they have some sort of a radar from the helicopters, right? So they shoot a wave and measure it, and they cover the whole of, they cover Switzerland in a grid, right? They cut it into a grid, cover Switzerland in a grid, they fly the helicopter along a straight line, measuring these reflections, and they tell you what the exact height is going to be. Of course, they can't do this precisely, right? So they are going to make errors. So this, and they exactly have this kind of error bars. They supply you with these error bars. So this is just a one-dimensional representation that at each point they tell you what is the mean value, and then they tell you what is going to, and these are independent measurements. So tell you what is going to be the mean plus standard deviation and the mean minus the standard deviation. And here is a synthetic example. So you have to do an interpolation because they only give you discrete values. So with Chris Schwab and a former student, we did that. And here is a description of a bottom topography or a digital terrain model with 962 random parameters. Okay, so slowly you can imagine that whole of Switzerland, how many random parameters would be there. So here is an example, a realization. It's a very simple topography. So you have a hill and a valley. And this is the mean plus standard deviation and the mean itself. But the point is that there is a clear description of these guys, and you have 962 of them. So the point is, you see, I started with just 2 parameters to describe the function, then we went to 11, then we went to 962, and you can go on like this. We have worked with models with more than 10 million parameters. So it could be that the number of ways in which you represent this uncertainty is very, very large. So this is one way to represent uncertainties, and engineers like this way because then you understand what exactly each parameter is. Mathematicians don't. Mathematicians like a different way. They use what are called Carhonen-Love expansions, some sort of a Fourier series or basis functions for the uncertainty. I don't want to spend too much of time on it, just quickly. So this is based on what is called a covariance operator or a covariance kernel. So f is your random field that you are interested in. Remember, it's a function. So x tells you how it varies in space, omega tells you the realization. So you can define what is called the covariance. So this is exactly this at different points. A correlation function. It will come back in a big way later on in the second part of the talk. And then, so this kind of a function is there. This is a map. Then using this as a kernel, you can define an integral operator, which is a compact self-adjoint operator from L2 to L2, whatever that is. But the point is that this is eigenvalues and eigenvectors. So you can think of this as sort of a grand way of writing a Fourier series. So grand way of writing a Fourier series in the sense that you have some mean value, which you have to specify. You have some basis functions. You have some eigenvalues here. So, and then you have some uncorrelated random variables, okay, and you have to truncate this. You have to truncate this to finitely many values, and mathematicians prefer things like this because there is a Fourier description of or a basis representation of your random field, and this can quickly become lots of parameters. Sometimes you can truncate it. So here is an example. So remember that the Burgers equation, the flux is going to be u squared over 2. I can say I don't know that, means why should it be u squared over 2? When you do a Carhonen-Love expansion based on a Gaussian process, so the covariance function is a negative exponential, and then you see that the eigenvalues of this Fourier representation, they die down very quickly. So you can truncate it with 3 parameters and still you get or 4 parameters, and you get a rather good representation, which is shown here. Is slightly different from u squared over 2, right? So you have this representation here, and these y's here are normally distributed random variables with unit variance. So these are ways to describe random fields. Engineers don't like it because then you don't know what there is no physical basis for these functions, right? But it's very common in geophysics because once you're looking at rock permeability, there is no physical basis of uncertainty there. So you do things like this. So the bottom line, there are different ways in which you represent the initial uncertainty as random fields. Now this is a sort of a dense slide, but I'll try to just give you the main message here. So once you say that your initial data is a random field, right? Remember what this random field is. It could be each time you make a draw, you get a function. Then your solution itself is going to be a random field. Okay, flux is also a random field here. So the flux, like here, it was uncertain, right? So I have to put a omega here. So this is a random field now. So there is some measurability condition. But the point is the solution is such that for each realization of this omega, it's a function of space and time. So just like earlier, the initial data, each draw was a function in space. Now it's a function in space and time. It satisfies a bunch of properties that you don't have to care about. The most important ones are that for each draw, or almost every draw, again coming back to the question that Sebastian asked, P almost everywhere, I changed notation again. For almost every draw, this is indeed a weak solution, and it satisfies the entropy condition. So what you're saying is that, for instance, let's think of this. It's Burgers equation. Each time I make a realization of this, I get a fixed Burgers equation because my omega or y in this case is fixed. Then your solution better be a solution. what you get is a entropy solution, right? So this is essentially what it is. It's a point-wise realization of this. There are other ways to think about it, but about 10 years back, together with my colleague Chris Schwab, we worked out an entire theory for this. In particular, we said that all that we are doing in this construction is that we are taking this function where we have a solution operator. Solution operator is the mapping. Give me an initial data, I have a solution. Give me an initial data, I have a solution. So this is what you do. For each realization of the initial data, you compose it with the solution operator, then you get this random entropy solution. So earlier we had entropy solutions, now because the solution is a random field, you have random entropy solutions. It was important to have this solution map, because the solution map is a continuous map, so you have measurability is guaranteed. It has a bunch of nice properties. So the bottom line is that there is a mathematical framework which tells you that there exists random entropy solutions, provided that you have a scalar conservation law. And this is for equations like this, there is a mathematical framework to describe the solution uncertainty. But remember that we need numerical methods, right? Okay, there is a solution that doesn't tell us anything. So let's look at, for instance, with uncertain initial data. So there are two players now. So that there is physical space-time, because we have space and time, but we also have the probability space, right? Because everything depends on the probability space. So for the physical space-time, we will use our classical finite volume method. That's why I introduced finite volume methods. So this is the finite volume method. Remember that the rate of change of this is given in terms of the fluxes. So this is the numerical method. For scalar conservation laws, we are really lucky because we can even have a rate of convergence. There is a CFL condition which relates these two guys. And what it tells you is that if, I don't know why tau is for both delta t and delta x. So there is a rate at which this guy approximates your underlying solution, and this rate could be 1 typically, because you have shock waves. So it's not better than 1 at least. And because of that, so this is important, so please follow me here. So for each deterministic simulation, this holds, right? So you have a rate of convergence. For to calculate this, to calculate the solution, I need to do some amount of computational work. And how much of computational work do I do? It is proportional to the number of mesh points I have and the number of time steps I have. Because just imagine that per mesh point you have some fixed number of arithmetic operations. The number of mesh points are given by delta x to the power minus d, because d is the dimension. So in one space dimension I have 1 over delta x mesh points, 2 I have 1 over delta x squared, 3 I have 1 over delta x cubed. And then because of the CFL condition, the number of time steps is proportional to the number of mesh points. So in terms of this big O, order of this, you have this kind of a relation here. So this is the amount of work that you do per every simulation. But the simulation itself has this error, so you can invert these two by eliminating delta x and saying how much work you need to get a certain amount of error. And this is very important. And the scaling here is given by this. So for instance, if you take a problem with shocks, S is at best 1. You have a second order scheme, S is at best 1, and you are in 2 space dimensions. So this is minus 1/3. So what does it mean? To half my error, I need to do 8 times more work. Okay? And this is fundamental. So we can't help it. These are the constraints that we are operating in. To half my work, I need to do 8 times, to half my error, I need to do 8 times more work. It could have been different. For instance, even in one space dimension, d equal to 1, if S was a half, which it is theoretically proven, it's even worse based on your result for unstructured grids, right? So it could be, even if just let's do some simulation here, right? It could be a half here, d is equal to 1, then it becomes 1/4, right? So to reduce the error by a half, you need to do 16 times more computational work. So this is an important consideration to apply. This is for the deterministic simulation. What do we do with the probability space, right? So we also have to discretize the probability space. The simplest way to discretize the probability space is to use what is called a Monte Carlo algorithm. Now all of you should have heard of the Monte Carlo algorithm. It's a very simple thing to do. So remember that for each draw of my initial data, for instance, I get a function, right? So all that it says is that I draw it m times, and these are independent, identically distributed. I draw it m times, so okay, fluxes here in this case, And for each of these initial data, I get a well defined problem, because now I have a fixed initial data. I can use my favorite finite volume method and I get a solution. I have indexed it with I, because I is the draw index and tau is the delta t delta x. And then to sample my statistics, for instance the mean value, I just add these things up and average them. This is Monte Carlo. So you draw a random number generator, have your initial realization, evolve your numerical method, add them up. You do, it's completely non-intrusive, you don't write new code. You simply use your old code, have a wrapper on top of it and add these together. For higher moments you have to just do the same. For instance, take the square of it and you get the second moment. So these are the sample statistics. Okay? So Monte Carlo is trivial in a way, but you'll see that you can't do better than it sometimes. We can do error analysis at some point. If I have the time, I'll do it in some detail in the last part of the lecture. But for the time being, all of you should know that the error of Monte Carlo, it scales as square root of the number of samples. Okay, this is central limit theorems. It scales always as square root of the number of samples. So now I have two sources of error. I discretize in space time. The error is going to be given by delta x to the power s. I discretize in probability space using Monte Carlo. So this is a root mean square error. So this is a square root. So these are my two sources of error. They are additive. There is no cancellation between them. And then of course to say that each of these error terms is the same, I need to have the following formula, that m, the number of samples, scales like 1 over or 2s times the number of mesh points essentially. And then remember that we have this accuracy versus work estimate, right? So this told you the amount of work that I need is given in terms of the number of samples, which is this guy here, times the work per each sample. So work per each sample was given by the formula here. Now because we have this uncertainty, we sample, so we have a m sitting here. Now the m was given by this, so then you add this up and this is what you get. Okay, and this formula is very interesting, because remember that for a deterministic simulation I had said in two space dimensions, so s was 1 and d was 2, so I had 1/3, so I had to do 8 times more work to half the error. Now on the other hand I have this, okay, so s is still 1, okay, d is still 2, so I have 1 here, I have 2 plus, so I have 3 here plus 2, so 1/5. So what does it mean? For the uncertainty quantification, for the deterministic simulation to half the error, I needed to do 8 times more work. Now on the other hand, I need to do 32 times more work. Okay? So why is that? That is because I have all the samples to draw, and each sample could be expensive, and because I have the number of samples is large, it is square root, right? The error is square root in the number of samples. So this is slow convergence, implies a very high computational cost. Later on in the course you will see some exact numbers, how high this computational cost is going to be. But for the time being, it shows that Monte Carlo is easy, you can do it, it converges, everything is good about it, but it's expensive. So this was for scalar conservation laws, which are just model problems, and I will soon take a little break in a minute, but I just want to, the aim is different, right? The aim is to do uncertainty quantification, not for scalar conservation laws, but for real problems, which is multidimensional systems of conservation laws. And just this was a sort of a warm-up exercise. We would model all the inputs by these random fields, so we would want these random entropy solutions. Somewhere we need to use the fact that the deterministic problem, the underlying problem, has a solution, and this is expressed by this requirement here, that there should be a data to solution map, which is a mapping between integrable functions to integrable functions. We needed a convergent numerical method. Look at the error estimate. We needed a convergent numerical method and with certain rate, so we need that. And finally, to do any chance of doing anything, we need more efficient alternatives to Monte Carlo. So these are the requirements. So we know how to model uncertainties, that's not a problem. In order to have some well-posed or underlying formulation, we need this solution map, because each time we draw, we solve, right? So we need that. We need a convergent numerical method, and of course to do anything, we need more efficient alternatives to Monte Carlo. So after the break, let's take a break now for 15 minutes roughly. So we are here 10 past, and then I will tell you whether we can do these things or not, right? We need all these three things to have any chance of doing it for real problems. Okay. Before we stop, are there some questions or you got? Yes. No, this is the theorem. The theorem says that S can't be better than 1/2, but in practice it is more close to 1. So the theorem is 1/2. Indeed, it is true that if you this is Kuznetsov, if you have a general BV function as your initial data and your solution is a generic BV function, then it is indeed 1/2. But our solutions are never generic BV. For instance, they could be piecewise smooth, then I think the best result is 0.909. In practice, this is close to 1. So even if it's a fifth order method, it's close to 1. Okay, so this doesn't help to have a fifth order method. Smooth solutions, it's 5, right? But as soon as you have discontinuities, then it's close to 1. So you cannot do better than 1. So this is important. So you'll see that 1 will be a dream in what we are going to look for. Yes, okay.
So are you sure it's the same as in those two estimates? Because in the Monte Carlo estimate, you rather look on the weak convergence to about the bias.
Yeah, but here I overestimated it by the deterministic term.
Yeah, but
So
in practice, do you see
no, you don't actually. If you look at the field, you don't. If you look at an observable, you do. And I will cover that in the last part of the lecture. So sometimes if you don't look at the whole field, if you look at an observable, you might get a better rate. For instance, I have seen examples where we compute the lift and the drag, and these objects converge with better than 1. You see, even though the field itself converged with half. Not half, but 0.8 or whatever, 0.9. So think of it as 1. Means 1 is sort of a hard bound in this case. This part of the lecture, so from now to the next 45-50 minutes, is sort of the most technical in some sense, because you will see new concepts coming in. I try to do it sort of gently and don't want to dive too much into the details, because otherwise there's a risk that you will get lost. So let us see if these things are true, right? So let us see if these things are true. Let's start with the idea. Are there convergent numerical methods for systems of conservation laws which satisfy an estimate like this? So on paper, no, right? Because there is no theorem which says that, okay, if you have a system of conservation laws like the compressible Euler equations in 2 space dimensions, is there any numerical method which satisfies an error estimate like this, or which converges to an entropy solution? On paper, there is no such method. Yet we compute, right? Just one of you was telling me that he's computing the lift and the drag. People have been doing this for 50, 60, 70 years. So we still compute. So how do we test convergence, right? So the way we do it is by benchmarking. So what do I mean? I picked up a scheme. So this was a scheme that I developed with Ulrich Feuerholm and Nathan Tadmo some years back. Just as an example, you could choose your favorite scheme here, okay? And I want to check if this scheme converges, right? Of course, I don't have a theorem which says that indeed this scheme converges. As you refine space and time, it converges to a solution. Instead, I test it on benchmarks. A common benchmark is what is called a radial short shock tube. So remember that the actual short shock tube is cylindrical, but if you cut it in 2D, it has radial symmetry, and this is what it happens. So these are 3 different grades: 128 squared, 512, 256 squared, 512 squared, and this is the density. So you can see that this is the outer shock wave, there is a contact discontinuity out here, and there is a rarefaction wave, and you can see that at least to the eye, it clearly converges. And to measure this convergence, I don't know the exact solution in this case, so I take the differences between these two guys, and I see at least that the difference starts converging, and we have what is called a Cauchy sequence. L1 is in L1 in the 1 norm in this particular case, and it actually converges with rate almost close to 1. So we are satisfied. We say, okay, we do this, we do a few more benchmarks, and we see that on paper there is some convergence. But then we go to reality. So here's an example of a computation that we do in our group on more realistic problem. This is in 3D. It is the simulation of some part of the atmosphere of what is called an exoplanet. The equations are very similar. There is some stratification. There is a little more real chemistry. But the point about the simulation, and the picture is really impressive, right? The point about the simulation is that it's unstructured grids, and this is a second order finite volume method, but it's per time step you have 10 billion degrees of freedom. This is what it is, right? It's 10 billion degrees of freedom per time step, and the cost of this simulation, this goes into one of the most powerful supercomputers, even more powerful than the one you guys have at Zürich, significantly more powerful than the one at Zürich. It still costs for a single simulation 10,000 node hours. So I have a scheme which worked very well for this sort of toy problem. It converges and so on. I'm bold enough to spend 10,000 node hours on a leadership class machine and get a computation like this, which looks nothing like my toy problem, right? So, and this is the problem with benchmarking. So we should be careful with benchmarking, and we all do it. We also teach it to the students to do it. Let us try a different example, a little more interesting example. So now what I'm going to do is I keep the same problem setup. So I'm still on a square. I have periodic boundary conditions, just like here also I had periodic boundary conditions. I have the Euler equations. I have exactly the same scheme. All that I change are the initial conditions. Okay. So now the initial conditions, this is what is called the Kelvin Helmholtz problem, a very well known problem. So this is the density. So you have low density, high density, low density. You have an interface here, and you have a shear. Okay. So you have a shear across there. This is a completely bona fide initial condition, means this is a bounded function, so this should work fine. And I repeat the same experiment, right? So I have 128 squared. This is how the solution looks like. You have these big vortices that are starting to shed because of the shear. And then I do this at 256 squared, right? And you can see the solution, 512 squared, 1024 squared. So each time I'm refining, just visually, I'm seeing a different solution, right? And then I go all the way down to the finest grid that we can compute on, which is a lot, which is 16,384 squared. So 16,384 squared, this is how my solution looks like. You have tiny vortices, you have big vortices, you have small vortices, you have a lot of mixing, a lot of and now, of course, repeat the same experiment. Take differences between these two guys, and then what do we get? So we have 10 levels of resolution, and you get a flat line. So between each mesh, there is no convergence whatsoever. Each time I'm refining, I'm getting a different structure. So this tells you that why we don't have a theorem, right? Why we don't have a theorem, but also in practice, this is by no means a difficult problem. So this shows that by and this will be very common when you do real simulations, refining resolutions, you have very small scale structures. Of course, one can say that you might have convergence, but it is very, very slow, double exponentially slow. But then if you don't see it to 2 to the power 14, 16,384, it's useless, and you'll never compute at 16,384, right? And the point is, whenever the flow becomes unstable, which is generic, turbulent, which is even more generic, you have this kind of a behavior that refining resolution gives you different answers. You have same behavior for many numerical methods. You can say, okay, this was your particular numerical method. You choose your numerical method and repeat this experiment. It's a very simple experiment. You'll get the same answer. And in fact, this tells you that this is not possible. You cannot have a convergent numerical method because I just showed you a numerical example where this doesn't satisfy. And in fact, this is completely attached to the first question here, where you needed a data to solution map. A data to solution map is also not possible because we know for a fact now, for instance, due to work by Dillelis, Sekelehi and others, that entropy solutions for multi-D systems are not going to be unique. So this is a mathematical theorem. There are examples where it is not going to be unique. So since they are not going to be unique, you cannot have a map between the solution and the data, because you have to have a map, means you map an input to a fixed output, right? You can't have that. So even the very basic consideration, if you look at nonlinear systems in multi-D, the first two go right out of the window. And there's no point to look at the third when the first two are not satisfied, right? So what can we do? We are stuck. In a way, right? Because with the basis of what we did for scalar conservation laws is completely demolished, even with very simple examples in two-dimensional systems. Yes?
So the simulation showed have the same initial conditions
Same initial condition.
And you just refine it.
Just refine. And then this is what you observe. No change in the initial condition. The same, exactly the same initial condition. Okay, so this is very bad news, right? What is the meaning of UQ? The interesting bit is that you can still do UQ. Let's try to see how. Okay, so this was the sort of the setup, right? And this is, I wanted to, somehow I have failed to copy this for the initial conditions. So this was the initial conditions. So you have an unstable interface, you saw why it is unstable. You have an interface between low density, high density, periodic boundary conditions. So I have to have low density here, and this is the shear, right? So the velocity goes like this. So you have the formation of shear. So now what you can do is, okay, how do you know that this is exactly the shape of the interface? Means if you try to do this experiment in reality, you'll never have the exact shape of the interface. You might have very, very tiny perturbations. You can also do them at the level of the grid, by the way. But let's say that you have very, very tiny perturbations. Let's try to do UQ the way we have learnt it. So how have we learnt it? We say that this, let's say for simplicity, that this interface is uncertain. So we will have small random perturbations of this interface, and for each draw, we simply run our numerical method and we average the answer. Okay? So now for a single draw, remember that these were 3 different resolutions. This is the picture that we get. There's no convergence between these two guys. Now this is what you saw. Now of course the interface is unstable, right? So I have tiny perturbations, and then I took 2 of them, just 2 of them, 2 perturbations, and add them up. Okay? So because what is Monte Carlo? You add up several samples. If you take 2 of them, add them up on the same grades, then again you don't see, okay, there is some averaging, but there is no convergence. It's still not convergent. I take 8 of these, okay, 8 samples, tiny perturbations. I add them up. You start seeing that some of these tiny small scale features that prevented convergence are getting averaged. You still don't get any convergence. If you take 64 of this, okay, now things get interesting, because when you take 64 of these tiny small perturbations, they start averaging. Okay, once they start averaging, you start seeing that on 3 different meshes you see the same picture, and when I take successive differences, I start getting convergence. If I take 1024 of this tiny perturbations, I really start seeing convergence. Now this guy here, the mean value converges. So what did I observe? If you take a single simulation, no convergence, right? And earlier my theory of UQ was based on taking lots and lots of single simulations, knowing that my single simulations converge, so lots and lots of them will also converge, and then doing the statistics based on that. But now my single simulation does not converge, but if I take lots and lots of it, it does converge. Yes?
When you say you sum up different simulations,
Yeah.
do you mean summing up different simulations with different grid?
No. On the same grid, all that you change is the initial location of the interface. Remember that you have this initial location of the interface, right? I even sort of discretized it to show you. On the next simulation, you change it slightly differently. Okay, just the initial location of the interface. You have the same grids, so you just take 10 of these and average them together. Yes?
Just out of curiosity,
Yes?
how do you randomly choose that from? Is it a uniform distribution?
Yeah, you'll see that it won't matter. So whatever.
Because the converged simulations, it looks like you have a uniform.
It looks, but it won't matter. It does not matter. By the way, I don't even have to do it randomly. I can also do it at the level of the grid. So, okay, let me just explain to you what do I mean by that, since everyone is interested in this. Okay, so remember that we have this interface, right? So we have a grid, we have this interface, so the interface could be somewhere here, right? So now when I do a grid, there is no reason to align my grid to the interface. I might, for instance, take it, one realization of the grid could be something like this. Another realization of the grid could be at slightly different value, right? Just put the grid slightly around the interface, okay? Then the sort of the cell averages will be slightly different, and that is good enough. That is good enough to get exactly the same results that I showed you. So you don't need any randomness except in this, no implicit, there is an implicit randomness because we have the grid. So there you don't need any randomness whatsoever for this simulation to hold. So what is the bottom line here? The bottom line here is, actually it's not surprising, right? Anyone who has learned fluid dynamics knows this, that for individual realizations, mess or chaos happens, whereas statistical quantities like the mean value, these converge. So you still seem to be able to do UQ, even though the deterministic simulation itself is problematic. Now the problem is that this is very nice at a heuristic level, you understand this at a heuristic level, but how do I put it down mathematically, how do I make it precise, and how do I sort of extract quantitative information out of it, right? And this becomes more mathematical, this is the most mathematical part of my talk, but I try to focus on the ideas rather than actual formulas. The first attempt to do so was actually done some years, 30, 40 years back by these gentlemen. They didn't think in this the way I think about it, but it was there in their work. It's by Diperna, Maida and people like that. And the idea is that they represented this uncertainty in terms of what are called Young measures. And let me try to explain what Young measures are. And let me explain this here with these pictures here. So the idea is, so now what's our classical notion of solutions of a PDE? Given space and time, you have a function, right? Given space and time, you have a function. Freeze time, just look at snapshots. So this is space, this is your function. Think of concentration, temperature, density, whatever. And at each point in space, or because you have weak solutions, almost every point in space, you have a single value. This is the idea of a solution. Now what Young measure does is slightly different. It says that at each point in space, you no longer have a single value. Instead, you have a range of values. And this range of values are weighted with respect to a probability distribution. So at each point, you have what are called PDFs, probability density functions. So here, you have a certain probability distribution. It says that you have a range of values, let's say from -1 to 1 or -1 to 2 with a certain probability distribution. Maybe there's uniform, maybe normal, whatever. At a different point, you have a different probability distribution. So think of it in terms of at each point in space and time, you no longer have a single value, you have probability distribution, and you stack these things together. And this is what is called a Young measure. Okay, mathematically this is what is called a Young measure. It's a measure on the phase space, because the phase space is where the values of density, pressure and velocity that you are taking. So it assigns a probability distribution, and it's a generalization of your notion of functions. Why? Because okay, it can happen that at one point you have a Dirac measure, one value with probability 1, or it can happen that at all points you have a Dirac measure with probability 1, then you are back here. So this is a generalization, that instead of having a unique value, you have a spread of values, a statistical spread. You have 1 point PDFs. And in fact, you can write it down, the equations can be written down. All that you have to do is you have to take the equation and you have to integrate with respect to the measure. So because it's a measure, so all that you can do with the measure is that you can integrate functions with respect to the measure, which is expressed here. And then you take the equation, you integrate with respect to the measure. So u, the measure is sitting in u, so this will be the identity. And this is f, so this is the action of the measure on f. So you get some PDE, not a closed PDE, but some PDE for the probability density function. Then you have an entropy condition, which is another PDE or a differential inequality, and this constitutes what is called a measure valued Cauchy problem. The object of interest is now a PDF. It's no longer one function. Okay, and what we did in this paper some years back is that this Monte Carlo algorithm that I had just told you, that you sample, you solve, and then you average, we actually proved rigorously that this, we call this as an ensemble Monte Carlo algorithm, right? So this was exactly the algorithm. You have this, you don't look at the deterministic solution anymore, you just look at the whole random solution, and we proved that it converges, and it converges in the particular sense that this not just observables or functions of interest, but rather statistics of these functions of interest, they will converge. Okay, so you can measure mean, you can measure variance and so on. This algorithm gives you convergent results, and this is what it does, right? So remember that we had this picture here, individual samples did not converge, but the mean value nicely converged. It was an admissible observable, so the theorem says that it should converge, which it did. The variance, now the variance is an interesting quantity. That also nicely converged, even though the individual thing did not converge. As you can see, it converges at rate 1, which is what it is. There's a little bit of a stall. We don't have enough samples here. And remember that what we wanted are PDFs, right? So we chose one point and we start with PDFs at time t equal to 2. This is on 128 squared grid, 256 squared grid, 512 squared grid, 1024 squared grid. Just to the eye, you can see that the PDF, there is a precise sense in which these PDFs converge, but just to the eye, we can see that these PDFs are going to converge. So this is great news. So now we can do UQ, but we don't have to rely on the deterministic simulations. We have even a theorem which says that this actually converges. So why is this working out? It's interesting to step back a little and think about it. Entropy solutions, these are weak solutions, right? So think of it as sort of space-time averages, right? Because this is what you're doing. You're taking averages in space and time. And these were the ones where the numerical scheme was not converging, the solutions were chaotic and so on. But with this measure valued solutions, in addition to space-time averaging, you're doing an additional averaging, which is you're averaging along the ensemble. So you have an additional source of averaging, and this allows you to realize these as limits of numerical methods. So that is great, right? So we have a framework by which we can quantify uncertainty and where we have a convergent numerical algorithm. There is a tiny weeny little problem, okay, which is a big problem. The problem is that this measure valued solution is never going to be unique. And this is problematic because in engineering we want a unique PDF, right? And there's no chance for this. It's never going to be unique. And here is an example. It's a very dramatic example. So you take the Burgers equation. Okay, this is as simple as that. Here we know that the entropy solutions are unique. We can even write down formulas, at least in simple cases. But now remember that my initial data can be a measure. It's no longer just a Dirac measure, it's a measure. So this is the initial data at a certain point in the domain. This is the initial data, same initial data. And then there are, you can write down just analytically two different solutions, two different PDFs in time. The PDFs have to evolve in time. So they have the same final answer. So instead of 0 to 1, they go to 1 to 2, uniformly distributed 1 to 2. In one case, they go abruptly because there is a shock which comes in and suddenly it changes from 1 to 2. In another case, you can construct a rarefaction, so gently you move the measure from one point to another. So this is not numerics, this is just analytical, it's a formula. So what does it tell you is that there is no chance, even if there is a convergent numerical method, even if you do this, there is no chance of getting a unique answer. So you might have multiple PDFs for the same problem. This is useless, right? Because this is just too little information. So however, so this seems to be too bad in a way, right? However, and this is, I think one of you asked this question, the solutions that we computed from the algorithm, from this Monte Carlo algorithm, there we didn't find multiple PDFs. In fact, we found a lot of stability. In what sense? So remember that I had these perturbations here, right? And I make different perturbations. I say that, okay, instead of changing the amplitude, I change the phase, or instead of changing the phase, I change the amplitude of this interface, or I take uniform, as you said, or I take normal. The mean value that I get looks exactly the same. The variance that I get looks exactly the same. So if these guys are so unstable, then we would never be able to get such stable results of a computation. What is even more striking is that I take two completely different numerical methods for conservation laws. One is this scheme that I told you, another is sort of a standard astrophysics code, and I compute the measure valued solutions. The mean and the variance are exactly the same. So whatever be the perturbation, I'm getting the same answer. Whatever be the numerical method, the source of approximation, I'm getting the same answer. So this suggests that what I'm computing cannot be a generic measure valued solution. The PDF that I'm computing is a stable object, and probably there are some additional selection criteria for the computed solution that I should find out, right? So this is a question. There must be additional selection criteria, otherwise we wouldn't be able to find that out. Maybe this is a good time to, if there are some questions, if you have some questions, I'd be happy to. This is a good, yes?
For the MCA approximations of the different means, do you reuse your samples or are the samples independent from the different grids?
No, it's the same sample. So the sample is always the same, but the grids are different. So on the same, you take the same sample. So for the mean you don't have to, right? Because you just have to average, but this is a choice that you make.
Okay,
So
use
Not in this particular, so there, at some point I'll change that. So for these experiments, this was exactly what you described, but in practice these are independent objects, so we'll use different sample sizes. There will be some estimates coming in which will tell you how many samples are necessary, okay? But to get the same kind of error, you need more samples on fine grids. Otherwise, it will the sample. You can see that already. So I think this is an example, right? So I have taken the same number of samples for the variance. In the beginning, I had sort of convergence of 1, but now the Monte Carlo error is somehow dominating, and I have a stall in convergence here. So this shows that I need more samples. Yes, you had a question. No?
So here, you're somehow getting the same final PDF, right? Maybe a question could be, what if we are not tweaking it enough? Maybe if we really change the boundary conditions.
But boundary conditions is periodic boundary conditions, right? So here all the uncertainty is in the initial conditions. Of course, in the boundary conditions is a different problem. So you cannot, of course, if you have different boundary conditions, you will get different answers. You should get different answers, right? So if you fix the boundary conditions and change the perturbation, you will get the same answer. So there is so you have to, if the boundary conditions change, the answers should be different, right? So this is not surprising.
And you're comparing these distributions only based on their mean, right?
No. We will see much more finer measures. We'll even put metrics on measures. So this will be much finer. You can see that already a bit. So this is the whole PDF, right? So now you can see only of the density, of course, in order to visualize it, you can see the PDF of the density, and you can see that this is okay to the eye. You'll see some quantitative answers later, but to the eye, this seemed to be approximating the same object at the end, right? So it will not just be the mean, but this, you raise a very good point, right? You'll see in a second why this is an important point. Any further questions? No? Okay, so bottom line, yes, Håkon.
So this ensemble of measure value solutions, everything that you sample is not well posed. You just take your black box over and you take a sample.
This is exactly what we do. So the algorithm was as before. You make your initial realization. For instance, let's look at this picture, right? Make your initial realization, okay, whatever, by also different gridding. Make your initial realization, use your numerical method, okay, use your numerical method. This is, of course, a numerical method is for a finite grid is always well posed. It's just a numerical method. Combine these guys together. Then what you're interested is in the limit as the number of samples goes to infinity and as the grid size goes to 0. This theorem tells you that this object, where is this theorem? This theorem tells you that this object is well posed or well defined. There is a limit object, and this limit is a measure valued solution which satisfies these equations. So this is the theorem. Yes? Yeah. Huh? Psi. Psi is any test function. So you choose psi. The functionals are, you want to express functionals, right? I think I was talking with one of you in the break, and this is the way I write a functional, that you have some g of, it could be square, it could be, if you want to compute the drag or the lift, think of it, right? Psi could be some penalization around the boundary, just some arbitrary test function. Okay, so the question that he asked is a very relevant one. We are searching for some additional criteria because the computation is very stable, and this is sort of a difficult slide to understand, but let me try to walk you through this. So what is this? So this measure valued solution is evolution for PDFs. So just take the scalar conservation law, which is Burger's equation, f can be quadratic. This is good enough. So now you integrate with respect to the measure. What it tells you is that this is nothing but the mean of the PDF. It tells you the rate of change of the mean is given by some rate of change of some flux, okay, integrated flux. This is one equation you have. Then you have a bound on the second moment because you have the entropy conditions. Entropy is a convex function, so this is, think of it as a square, okay. So, and you know that this is inequality, so you have a bound on the second moment. So the equations that I get to constrain my 1-point PDF are an evolution equation on a mean and a bound, not equality but a bound on the second moment. And this is exactly the point, because all of you should know this, that if I just tell you the mean and I tell you a bound on the second moment, It does not specify any measure uniquely. You just take the same mean and the same second moment and you change the measure on the higher moments, right? So there is no chance of any uniqueness simply because we want to determine the whole PDF, the whole measure, and all that we are doing is we are constraining the mean and we are constraining the second moment. This is not good enough. So what would have worked, and this is the main reason for the non-uniqueness, that there is not enough information given to the system. On the other hand, if I would have had some arbitrary moments or arbitrary test functions here, eta is an arbitrary moment. Think of it as an arbitrary moment. It's actually an arbitrary test function. And if I had information about this, all moments, then maybe the PDF can be specified, right, under certain conditions. And we do that. So we calculate, instead of this, for a scalar conservation law, we calculate this with respect to this eta. This is a completely formal calculation. So in fact, I have used a random field to illustrate. And this is a long calculation, things go okay, but of course I put a term in red. This is the term that shows up. And what does it tell you? To specify a 1-point PDF, which is to specify any arbitrary test function, I need, of course, things happening at those points, but in addition, I need an object which I have put in red here. And this is a very important object, because it tells me to specify the 1-point PDF at the point x, forget time for the time being. I need information, statistical information, because I am integrating with respect to a probability measure. I need statistical information at the point x, which is okay, of course it should. But in addition, I need statistical information at nearby points. Okay, so in order to calculate a 1-point PDF, I need information about, statistical information about the function at that point. I need statistical information about function at other points, 2 different points. And these are precisely what are called correlations. Let me try to explain this in terms of picture. So measure valued solutions is 1-point PDF. You have 1-point PDF sitting here, we have a 1-point PDF sitting here. And this satisfies some equations. It has to be consistent with the PDE. But to find this, to uniquely, this simple calculation, which I don't have time to explain in detail, what it tells you at the bottom line is that I need information, statistical information, about 2-point PDFs, or 2-point joint PDFs, correlations, because it's a non-linear problem. If it was linear, it wouldn't be. But I need 2-point PDFs. So to specify a 1-point PDF, I need joint probabilities. Okay, joint probabilities is fine, but then let's put in the joint probabilities. This is an iterative calculation. If I had a joint probability, 2-point PDFs, then to specify these uniquely, I would need 3-point PDFs, and I would need 4-point PDFs, and I would need 5-point PDFs, and so on. This is completely due to the non-linearity. So yes?
I did not follow, I didn't understand what is a 2-point PDF.
A 2-point PDF is simply the, okay, let's, heuristically, it is the probability given a value here, what is the probability that you get a value here. Okay, so it's a probability on two directions. So the value is here and the value is here. If you want to draw it as a histogram, you will have two. Yeah, if you want to draw it as a histogram, it will be a 2-dimensional histogram, right? It's a conditional probability. Yes, I should have said very clearly. It's a conditional probability. So 1-point PDF, which is just the probability density function at 1 point, you need 2-point conditional probabilities. To determine this, you need 3-point conditional probabilities. To determine them, you need 4-point conditional probabilities. And then you have the sea of conditional probabilities that you have to deal with. Cannot avoid it because this is nonlinear. This is the whole point of nonlinearities is this. And non-smoothness, because if this was a Lifshitz function, we could pass to the limit and do something. Why? Because if the function is smooth, then what happens at x can predict what happens at nearby points. But if the function is not smooth, you cannot make that prediction anymore. So 2 things come together, the non-linearity and the lack of smoothness. And because of that, we have to deal with this lots of joint probability density functions. Actually, we were brave enough to do that some years back, and this becomes the most sort of complicated part of the lecture. Let me try to explain this a little bit heuristically. So again, they are young measures, but coming back to your question, Sebastian, one should think of these objects simply as this joint probability density functions. Okay, these are just joint probability density functions. We need a bunch of conditions on them to make them well posed. In particular, we need some information about what happens at small scales. Means if you have very bad, if the joint probabilities are such that what happens at this point and what happens at nearby points are very, very different from each other, you can't handle it. So you need some information about some consistency between them. So this is what is called a hierarchy. Means it's so remember that these objects, the joint PDFs, these are defined on tensor product spaces. So you have product spaces on which it is defined, and it turns out. So let me cut a long story short. That these objects, this what are called correlation measures, joint PDFs, all possible finitely many points, they all can be expressed rather succinctly in terms of a single object, and this single object is a probability measure, but on functions. Okay, so now we are heading towards the real crux of the matter. So what is the meaning of a probability measure on functions? It's not hard to imagine that, right? So remember, so I have drawn a bunch of functions here. So one is in green, other is in red, in blue, yellow, and so on. A probability measure on functions simply assigns a weight to each function. So earlier, a probability measure on points assigned a weight at different weight at each point, a different weight at each point, and so on. Now what I am saying is, I have a probability of 0.2 of seeing the green function, 0.1 of seeing the orange function, 0.1 of seeing the yellow function, and so on. So this is a generalization of the classical notion of functions. It turns out that all these correlations, multi-point information can be absorbed in the single object. Of course, the risk or the sort of the payoff is that you have to deal with the probability measure on an infinite dimensional space, because functions have infinite degrees of freedom, right? So these objects, they completely describe all these correlations. And another way of thinking about it is, so you have functions here. It could so happen that all your probability is concentrated on a single function. For instance, the green function has probability 1. Then you're back to your classical notion of functions. So this is a generalization of the classical notion of functions, and this leads to, and there is also a theorem. So there is a very precise way in which all these correlations are expressed in terms of these probability measure on functions, and also we proved that just by knowing the moments, so these sort of tensor product moments, these are just products, you can determine this probability measure on functions uniquely. So this is the theorem. But what has this got to do with the PDE? So now we have a probability measure on functions. Earlier, so we started out just by saying functions. Then, okay, we said we can't deal with functions, we have random fields because of uncertainty, then we can't use random fields. We had PDFs at a single point, which one can think about. But now you are saying that we have probability measures on functions. So what's the connection? So let's, how is it connected to the PDE? It is connected to the PDE in a very natural way. Because so what is so the concept of solutions that we define it are called statistical solutions, which was one of my keywords in the title. So this is a probability measure on functions. For instance, P is 1, you have integrable functions, or P is 2, square integrable functions. And now remember that to define this uniquely, so time is just a parameter. So it's like you have been given an initial probability measure on functions and you evolve it, okay? So this evolution has to be constrained by the PDE, and there's a very natural way to do that, because all that you have to do, remember that we look at these kind of moments. For a scalar problem, these are just products, okay? You don't have to think about tensor products. This is for systems, right? You have vector, so you have to multiply them, you need tensors. But the solution of this, smooth solutions, they are going to satisfy these kind of formulas, right? Because you want the value at point x1, you want the value at point x2. This is the evolution equation. The point is that this can be done for multiple points, this can be done for weak solutions, this can be done for arbitrary moments, and this can be done for measures. So this is a 50-page paper to do that, but this can be done. And what you obtain ultimately is that, okay, you have this probability measure on functions, but it is constrained in a rather severe manner in the following way, that all these moments have to satisfy this sort of a infinite family of PDEs. Each of these PDE is sitting on tensor product domains. It's an infinite family of PDEs, but each of them is finite dimensional. And for those who know statistical physics, I don't expect all of you to know this, but those who know, this is what is called a BBJKY hierarchy. So in the classical mechanics, this will be the Liouville equation, the infinite dimensional object. The finite dimensional family is this BBJKY hierarchy. But what is the connection with what we have seen so far? And this is so there is this object which satisfies a bunch of PDEs. how do we relate it? So remember that I told you that by just taking a Dirac measure, saying that the entire probability is concentrated on a single function, I'm back to weak solutions, and this is exactly what happens. If it's a Dirac measure, then this is a weak solution. Okay, nothing. This is a generalization of that. Now, what about measure valued solutions? Since this is a hierarchy, the first moment of it is your classical Young measure at 1 point PDF, and it is indeed a measure valued solution. So this is very much incorporated in it. So what you should think of in statistical solutions is that it's a measure valued solution as before, 1 point PDFs, but now you tell the system all possible correlations. Okay, all possible correlations, they are contained in it. So they are all possible multi-point correlations. So a priori, it is much stronger than a measure valued solution, because in addition to 1 point PDF, the system knows what is a 2 point correlation, the system knows what is a 3 point correlation, the system knows what is a 4 point correlation, and so on. And not only that, remember you had this random entropy solutions, for instance for scalar conservation laws. So this guy here, formally, this can be made rigorous, is the law of the random entropy solution, if it exists. A problem with random entropy solution is that it may not exist. So if you take the law of this, which is given by this expression here, you are back to the statistical solution. So statistical solution contains a lot of usual things. It's a generalization of weak solutions, it puts a lot of information on measure valued solutions, and it's the law of the random entropy solution. So this is the object that I claim is the right way to do UQ, or even to think in terms of well-posedness for systems of conservation laws. But this seems a very abstract thing at the moment, right? So let me again summarize. Think in terms of PDFs. These are familiar objects, everyone can think in terms of PDFs, but in addition you have correlations. So you have joint PDFs, multiple PDFs, and so on, and there's a bunch of equations that these guys satisfy. That is a statistical solution. But of course, how do I compute this statistical solution? So far I have just shown you how to compute a 1 point PDF, right? I have not shown you anything beyond that. That is going to be the next step. But if there is any question, this is by far the hardest part. After this it becomes easier. So ask, yeah.
What is
A is just a set. So what is a probability measure? A probability measure is on the set, you tell what is the probability of a certain set, right? So a certain set contained inside functions, what is the probability measure of that is given in terms of this push forward, right? So this is the definition of the law of an infinite dimensional or any probability space. Yes, further questions? Or okay, we will see it more concretely when I actually show you some examples of this. But this, as I said, was the hardest part of it. It is not enough to compute 1 point PDFs. You also have to compute, or you have to understand correlations, because they exist together. And this is sort of the key bottom line. Okay, so yes. Oh yeah.
Very irrelevant, but
Yeah.
you talked about joint probability density functions. Did you look into maybe, I don't know if it's relevant here, but something like joint normal distribution and Gaussian process?
Yeah, they are relevant if you input your input, because you also have to put an input, right? So your initial data, you have to put some sort of a probability measure on that. So a natural thing would be to put a Gaussian random field or a Gaussian process there, but evolution is highly nonlinear, so it doesn't remain Gaussian at all. But they are very natural in this context, because you have to put some initial measure on your on L2 functions, for instance. Why not a Gaussian random field or a Gaussian measure? They are very relevant. Okay, it's not irrelevant at all. Means this is depending on how you model your initial uncertainty, right? And this is an important point. Things will become clearer when I tell you how we compute these statistical solutions, because now I'm going to tell you how to compute them. It turns out that you compute them exactly the same way as you computed your measure valued solutions, by your Monte Carlo algorithm. That's why that algorithm was so stable, right? So this is, it comes from this paper that I told you, but it's a very simple algorithm. It's a Monte Carlo algorithm. So you have an initial measure, but now of course this initial measure has to be a probability measure on functions. For instance, a Gaussian random measure, or it can be given in terms of finitely many parameters, random fields, and so on. Once you have this measure, you should be able to sample from this measure, right? This is what we were doing. We are always able to sample from the measure. So for each draw, we get a function. That's the whole point of this measure, that for each draw we get a L2 or L1 function. Now we use my numerical solution operator. So this is the initial measure is written in terms or approximated in terms of this Monte Carlo approximation, the empirical measure. Then I have a numerical method. With the numerical method I can always evolve things, I evolve it, and then I approximate, I take an empirical measure, so I average these things together for the at time t with the mesh resolution delta with the number of Monte Carlo samples m. So this object here is a probability measure on functions, and this will be my candidate for an approximate statistical solution. This is exactly the algorithm that we did before. We sampled, then we solved numerically, and then we put them together in the form of an ensemble. So this remains the same. Now this guy, the question is, as delta goes to 0, as m goes to infinity, as you refine your grid, and as the number of Monte Carlo samples is larger and larger, are you approximating a statistical solution, right? So we have to now deal with a measure, or we have to deal with convergence in the space of measures. Of course I can tell you it works, but let me explain a little bit why it works, right? And now we come to more mathematical. I am a mathematician, so you have to be precise in what you say. So now you have to deal with some topology or some convergence, notion of convergence of these objects, right? And there is a natural topology. You see there are several papers here about that. There is a natural topology on measures, but we also have some dependence in time. So there is a natural topology on that, but this is very difficult to work in this topology. So you need some sort of sufficient conditions. So let me try to explain to you. This is simple. So what we are saying is the following, that as long as this measure here, or as long as the underlying numerical method satisfies the following conditions. So you need uniform LP bounds, so you need some uniform integrability. In particular, you say that the solution that you compute is bounded in L2. This is if it blows up there, then your scheme is bad, right? So you have a stable numerical method. But the more critical one, those who know turbulence might have seen this object called structure function. So this structure function, this tells you about correlations at small scales. So this has to behave in some nice manner, okay? In particular, as you shrink objects together, the correlation has to converge to the 1-point probability density function, and it has to happen uniformly with respect to this delta. If these conditions are satisfied, the theorem says that you have some convergence in a very precise sense that I am going to tell you later. But how do we check that these conditions are satisfied? So I told you that your numerical method has to be stable. So in particular, it has to satisfy discrete entropy inequality. If it does, then the first condition is satisfied. You have bounds. So you can, the first condition is satisfied, you get a probability measure. Then for the second condition, one has to be very careful. So as I said, there is no bound, and you don't even see it in practice, on the derivatives, because as you refine, you get worse and worse, you get more and more turbulence somehow, smaller and smaller structures, so derivatives are going to blow up. So whatever worked for scalar theory, BV bounds, they don't work. So any object on the derivative, this is a derivative, somehow it measures the variation, right? This is going to blow up, okay? What you can control, S is the order of your scheme, you can control the rate at which it blows up. Because you can control that, this you can prove. You can control that, the structure function, which tells you correlation at small scales, at the level of the grid, you are able to control this quantity. So that is great. However, and you don't care what happens at large scales. As in turbulence, the problem is always at intermediate scales, and at intermediate scales you have no information, right? So small scales you have control, large scales you don't care. At intermediate scales, relative to the grid, you have no control. So we had to make an assumption. This assumption was inspired by what Kolmogorov had in his famous theory of turbulence, which some of you might know about, and it's an assumption on scaling. It's a weaker version of this, but it's an assumption nevertheless. It says that if there is some scaling, then you have some uniform control on the structure function, and the conditions of this theorem are satisfied. And this scaling, I'm not worried about this assumption, because in every practical situation this seems to be true. It's difficult to prove though. Then you have convergence of these objects to a statistical solution. So now, what is the meaning of convergence of these objects to a statistical solution? This means that not just 1-point statistics of interest, but any multi-point statistical quantity of interest. So K is the multi-point here, that is why you have this product domain, G is some arbitrary functional, these objects are going to converge. Coming back to sort of engineering practice, what it means is that the mean should converge, the variance should converge, higher moment should converge, point PDFs should converge. So these are 1 point statistics, at each point this happens. But now 2 point statistics, so remember that I had this structure function, this is the object that is very important in turbulence literature and also important in our theory. This will converge, the spectrum, which is nothing but the Fourier transform of this object, will also converge, multi-point correlations will converge, and this is the beauty of this thing. So remember that we saw, and we couldn't prove, but we saw that all deterministic quantities did not converge, the field never converged. Now under this assumption, we prove that any statistical quantity that you write down will converge. So this is sort of there is a massive difference when you look at it deterministically, when you look at it statistically. Any quantity that is reasonable within the bounds of the system is going to converge. Spectra are going to converge, structure functions are going to converge, mean, variance, PDFs, joint PDFs, all of these quantities are going to converge. Okay, so there is a convergence theory, it works, it's sort of mathematically rather detailed, but the bottom line, the results that you get out of it are really striking given the non-convergence. And we will see this in practice in a bit, but this is again a good time to ask questions if there are any. Come on, I'm sure that all of you did not understand everything, right? So you have to show that you understood something by asking. Okay, let me summarize it again. Forget about the mathematical details. The bottom line is exactly this slide. Under reasonable assumptions on your numerical method and your underlying flow, many of them are verifiable, some of them are, all of them are verifiable. The difference is that you might not be able to prove one of them. You are able to prove that this algorithm, Monte Carlo algorithm, it converges with respect to every single statistical quantity. Okay, let us try to see this. So remember, we go, yes?
So what was your epsilon and was it both parameters?
Both parameters. That's the reason why I put an epsilon there.
But you had to balance those parameters.
For a convergence rate, otherwise m has to go to infinity and delta has to go to 0.
Okay.
So there is no, so far this is just means it's a convergence theorem. It says as you refine your grid and as you let your number of parameters go to 0, you can actually change the order between them. So it's not important. There is no dependence between them, but this it has to hold that m has to go to infinity and delta has to go to 0, and I put it in epsilon. I'm sorry. So epsilon is like 1 over m, but to put so there's already a k, which is the number of correlation points, and then if I also had a delta and a m, it would be too much. But that was the point. Okay, let's look at some examples, right? So Kelvin Helmholtz, we have already seen this. 1 point PDFs are very much covered by this theory. So of course you have nice convergence, mean and variance, as we saw before. This is very much. Now comes the interesting bits, right? 2 point statistical quantities of interest. So you compute this structure function. What was this structure function? This was this whole object here. So essentially what it does is that it takes 2 neighboring points, calculates the correlations, weighs them in an average, takes it over all points and over all time steps, and then you get this kind of a quantity. It tells you local correlations. This is the quantity on different grids. So now this is a function of r, right, because it depends on a scale, and you can see that of course when you take differences between this, there is very nice convergence. And because the correlation function converges, the structure function converges, all the assumption of the theory are satisfied, and you should have convergence very nicely. What is even more interesting is the following, because this is, I think someone asked about this, right? So now we have measures on function again. Sorry.
Something dropped. I could hear it.
Oh, really? Oh, now. Okay. So this was the reason. I hope it will recover very quickly. No? Something is happening. Yeah, sorry. I think I probably stepped on it and then it, yeah. Okay, so now remember that we have measures in infinite dimensions, right, on functions. Measures, you can't have a norm on measures. Measures are not normed, right? Functions are normed. But measures have metrics on them. And one very popular metric, which I don't go into details, is what is called the Wasserstein metric. It's very popular these days in statistics, machine learning, and so on. So you can, so the convergence that we have, the theorem that we have, it automatically implies convergence with respect to this Wasserstein metric, okay, on probability measures. But of course, you can't compute infinite dimensional, the Wasserstein metric on infinite dimensional measures. But remember that this probability measure here is 1-point PDFs, 2-point correlations, 3-point correlations, and so on. Everything is contained in that. So you can compute those marginals. So you compute a Wasserstein metric between two PDFs and then sum them over all space points. You compute two-dimensional Wasserstein metric over 2 points and so on. This you can compute. So the theorem says that there is indeed convergence, and indeed, as you can see, that there is very nice convergence between these 2-point correlation measures, and you observe this as you refine. So this tells you every single 2-point statistical quantity of interest will converge, because the metric itself converges. So you have a lot more information there. And this is what, coming back, this is a visualization of the joint PDF. So you take 2 points in the domain. I think 1 point was taken here and 1 point was taken somewhere here. And now you look at just the density for visualization purposes. So value of the density, and this is the sort of histogram, right? It tells you some places there is more probability, some places there is no probability, and so on. And this is over a sequence of grids, 128 squared, 256 squared, 512 squared, 1024 squared. Of course, we have seen that the metric converges, so this just sort of further endorses this convergence. So even these objects are computable and they converge. Okay, so this is neat, right? Here's another example which is quite striking. This is what is called Rickmeyer-Meshkov. So you have an initial density bubble, and there is an explosion, and then you get some very complicated evolution. So this is at time t equal to 4. So we have periodic boundary conditions. Shock waves come in and they interact. So this is on a sequence of grids. Just the one sample, this is in density. You can see the solution gets more and more complicated. Of course, there is no real convergence, right? But again, the assumptions of our theory are completely satisfied in this case. So the mean very nicely converges, as you can see. The variance converges. Structure functions, they are even sitting on top of each other, so they clearly converge very nicely. And this Wasserstein convergence, right? So this Wasserstein metric for 1-point correlations, very neat convergence. For 2-point correlations, very neat convergence. So not just the 1-point PDFs converge, even the 2-point PDF. We have also done 3 and 4-point, and everything converged in this particular case, because the theory is already there, right? There is a theorem which says that it should converge if your structure function converges. So that was the thing about it. And this is the 1-point and 2-point PDFs. At some points, you can see the 1-point PDF, it sort of slowly converges, but it converges towards the same thing. The 2-point joint PDF, just like before, this one is not very representative, but once you get to 512, 1024, you really see that there is even eye-level convergence. But of course, you have this. So this will automatically imply that this converges, even if you don't see it on the eye level. So we have many examples like this, and in every single example we found that the theory was validated. And this is another example. Okay, this is a fun example because it tells you how many stochastic parameters can be. So here density and pressure are initially uniform, but the velocities, there are two components of it. This we take even Brownian or fractional Brownian motion. So this is a realization, right? So fractional Brownian motion means we have lots and lots of parameters. The structure function, because the mean and variance are not interesting, again the structure function very neatly converges, as you can see. So the assumptions of the theory are satisfied, and this is for the 2-point Wasserstein metric, and you can see a very neat first order convergence. So even though the deterministic thing is this is almost noise, right? But still the statistical quantities are very well behaved in this particular case. So bottom line is, in every single thing that we have checked this theory very nicely converges. So you can do UQ. So remember that we had this picture here where we had the data to solution map and the convergent numerical scheme. For systems, we don't have this, right? Somehow the two are compressed together. The UQ is still well posed, okay? But of course, because of the statistical solutions and so on, of course, we still need more efficient alternatives to Monte Carlo, and this is what I'm going to talk about in the next part of the lecture. So I think it's time to take another break, because this was heavy duty. The next part is light. Okay, so it sort of it goes up like a normal distribution, then there's a peak, and then towards the end it will be completely easy. So so we saw that, and the interesting thing is that so the bottom line so far is, if you have a Monte Carlo algorithm, and if you do this kind of computations, then you have convergence. But let me focus a little bit on the computational challenge. There are many theoretical challenges, but the computational challenge is the most interesting one, right? So for this audience at least. So the Monte Carlo, the problem with Monte Carlo is that it's expensive, right? So the convergence rate is 1 over square root of m, non-improvable. And let's translate it a bit into numbers. So for 1024, now we are talking 3D, because 2D we are able to do this, right? For 3D, you take 1024 cubed, this is the highest resolution we wanted to compute. And for 10 years now, starting in Oslo, where I met Håkon, I was more than 10 years, 15 years almost, we have been developing this code. It's sort of a very good Cartesian grade, finite volume, high resolution solver. And the hardware is this one, PISDAINT, which is the most powerful supercomputer in Europe. It's the world's 6th fastest computer. And even on that, a single sample takes 3000 node hours. 3000 node hours, which is okay what it is. But the point is, a single sample gives us no information, right? The whole point of this is that you have to run multiple samples. If you do 1000 samples, which is what we did in 2D, all these calculations are with 1000 samples at 1024 squared. So if you do the same, then, and if you start costing it, so this will be the cost, $1.7 million. Okay, so 1.7 million is a lot of money to burn on a single uncertainty quantification simulation. So we did this calculation about a few years back, and I told my PhD students that we need a factor of at least 100. A factor of 100 would get us down from 1.7 million to 17,000, which is still expensive, but it is affordable for a single run. So what do we do in that respect? So I have a student, PhD student, who's just finishing now, Shepin Lie. What he did is he realized very quickly that the reason why we are slow on this machine is because our code is sort of CPU based. Bulk of the computing power of this machine comes from GPUs. So you have to do a translation between the CPU code and a GPU one, but it's not so easy to do a multi-GPU code, particularly in 3D. But he wrote one all by himself, and it's custom made, highly efficient. Why is it efficient? Because it has very good scaling. You can see that it really scales to many nodes on the system. It has very good memory properties. Problems are memory bounded, finite volume, finite element, all these methods are memory bounded, and we reach, for a single GPU, we reach about 60%, and it scales very well. So this is very good. Also in terms of the number of flops, it's very good. So just by doing this, we were able to get a speed up of a factor of 10 to 20. So out of that 100, at least a square root is shaved off just by doing that. And we also have excellent visualization and I/O support from a current PhD student, Ramona Hall, and we are really able to do 3D simulations even with Monte Carlo, because we got the cost down. So here is an example. I'll show you at least one movie, because I'm very proud of it. So here is the single sample, I think, yeah. So this is the Kelvin Helmholtz problem, but in a tube. So you have high density, low density, and then you have some shear at the edge here, and this is a simulation at 17. Oh, my computing, my battery power is really going. So it's 1792 cubed. Okay, this is a big simulation, but it's a single simulation, 343 nodes on that machine. So this is a serious simulation. And this is how the solution looks like. You're looking at the density, you're looking at iso volumes, isosurfaces, and you can see how the density evolves, right? So you can see that there are the smaller and smaller eddies which are formed. It really looks like a jet or smoke or something like that. It has a lot of spatial structure. It's a beautiful simulation, but as we know, this is a useless simulation because there's no convergence. If I do it at 2792, I'll get a different result. So then we were, we were able to compute this with, so we computed the mean and the variance at a lower resolution, of course, and here is the mean. This is at 512 cubed. Again, oh gosh. You know what, I think one of the reasons why it is doing that is because my battery power is running low. Now of course I don't even find my, but I did take out, see, I even have it here and I don't run it. It's sort of crazy. Just give me 1 second and then I do this and then I do this. I hope this will fit here. And this one, I think I keep on stepping on something and that's the reason why. No? Oh, of course the movie is playing, but let's stop it. So now we visualize the mean, okay? And this is a non-trivial computational problem because we have done it with 512 samples. Now you can imagine each sample is 512 cubed, so how much of data is involved? And no one has been able to produce movies in 3D of things, and you need at least 100 times snapshots, right? So you need a massive sort of data compression, and this was done by some in situ online visualization using Catalyst, and I can show you how the mean evolves. So you can see that the evolution of the mean is much more boring, right? But that's good because it's computable. Boring is good. The solution structure was very complicated, but the mean evolves in a much more gentler, nicer fashion. It's visualized on several GPUs. That's why you see that line there. So this was the mean, and you could also see, so this was the single sample, and just let me, I don't understand, and I'll show you the variance. It's also, it has a much more, why didn't it work? It has a much more gentler evolution, as you can see. So this is the variance. It still has more structure than the mean though, and again it evolves very nicely with, this is on 512 cubed with 512 samples. And what is very interesting is we can also visualize point probability density functions and 2-point probability density functions. So here's interesting bit. So here is a point probability density function initially, and now in density, right? Now we can visualize what happens as a function of time, and this is what it is now. Fat chance of ever being able to write a formula. But the point is, this is a well-posed computation. We know that this computation converges because, so this is how the point probability density function moves. This is at a different point. And again, it's a very non-linear evolution of the histogram. It has different values and it takes different values in the different bins here. And what is most interesting is a 2-point probability density function. Okay, so these are the 2 points at which we saw the point probability density function. Now this is the joint probabilities, and now you can see that the histograms, they have a very non-linear evolution. It's difficult to write down an equation to describe them. This is done from the Monte Carlo simulation, and you can see that there is a rich structure of that. Right? It's difficult to write down formulas or describe this in some analytical way, but we know that the numerical simulation converges, so there is a theorem behind it, and then we just do simulations like this. It looks cool, right, to be able to actually show a evolving 2-point histogram, but it's possible because of this highly efficient visualization. So we can do 3D simulations already. Okay, so here is the same problem that you saw. Of course, individual simulation is useless, it doesn't converge. The mean converges very nicely at a very high rate, 1.3. I don't know why this happens. Variance doesn't converge so nicely, it has more structure and it converges. Structure functions, this also very nicely converge. Wasserstein metric, we can compute this also in 3D. There is a nice convergence in 1-point correlations, 2-point correlations. Is another problem, the Meshkov problem in 3D. The bubble explodes, and you can see that these are the shocks, and this is again isosurface visualization. Very complicated structure in this ball here. It's like a turbulent ball evolving. No convergence. The mean, on the other hand, converges very nicely, as does the variance. as do the structure functions. They have very little variance in the structure functions themselves, as do the Wasserstein metric. So all the quantities that you saw in 2D also work in 3D, except that now the computational cost is much higher, right? And even then, remember that I had asked for 100 and we got 10. There's still a factor of 10 missing. And this is the reason why I don't show you these simulations at 1024 cubed. Okay, here actually it is the 1024 cubed for the, but at least here I don't show you, I also show you up to 512 cubed because 1024 cubed was still not affordable. So we need, and with hardware we can't get any more. This was sort of the limit with the hardware. We have access to a very powerful supercomputer, we have very good algorithm, and this is the best we can do. So maybe in the future the hardware becomes better. So we really need new algorithms, right? And one of the algorithms I'll quickly walk you through is the multi-level algorithms. Actually, Håkon is someone who has worked quite a bit on multi-level algorithms. And maybe you should teach a course on that so that they learn what it is. I had sort of prepared some extensive notes to do it on the blackboard, but I think maybe we are all too tired and it will take a long time. Let me just give you a gist of what multi-level algorithms are so that you understand the basic idea. So who tells me that I have to use exactly, so what, for instance, even in this 3D simulations, what do? This is one sample at 512 cubed, I take another sample at 512 cubed, I take a ton of samples at 512 cubed and I average them. This is the mean, and from the average I compute the variance, right? And then I do the convergence. Multi-level algorithms, what they do is that they want to use information not at one mesh resolution, but at several mesh resolutions. Okay, this is sort of the beauty of them. They were developed in this context by Heinrich and later by Giles. Many other people have worked on it afterwards, and they come from the multi-grid methods. All of you should know what multi-grid methods are, so they come from that. And the idea is very simple. So you have a sequence of grids, nested for simplicity, you can also do unnested. So it's a fine grid, a coarser grid and the coarsest grid. And the idea is that I'm going to do my sampling not just at one grid resolution as before, but at all these grid resolutions. In particular, by keeping in mind that I will have a few samples on the fine grid because it's expensive, and I can have a lot of samples on the coarse grid where it is very cheap. Okay, so what it does is that it essentially combines simulations on different grid resolutions. Maybe I explain this a little bit, otherwise it doesn't become. So the idea is the following. So now maybe I focus on functionals and not on fields. So what is the meaning of functionals? So you have a function. Okay, so let's try to do it like this. So what is a computable quantity? A computable quantity, let's say 1-point statistics for simplicity. You can do the same with multi-point statistics. 1-point statistics are objects which look something like this. So you have the integral over dt, d is the domain, t is the time. Okay, maybe I keep it separate. So you have objects which are, this is your function space, LP of t, you have d, you have some psi, test function, psi of xt, then you have g of u of xt for that matter, dx, d mu t of u dt. So these are exactly the objects that are computable, right? Because this is what were admissible functionals. Now this is the way we approximate them is the following. So we say that okay, they are approximated by a numerical method, right? So we still have this, still the functional, this maybe we need to approximate this, but here I use my discrete solution operator S delta t of my initial data. Okay, take my initial data, plug it into the discrete numerical method, calculate this, and then calculate this object here dx dt of t mu bar. Okay, mu bar was my initial measure. Remember that we had this initial measure. By the way, can you guys see this, or is it okay? No? How do I ensure that you see this? That would be, that's not a good idea, is it?
You can just bring it down a bit, like, so that the project is not projected to the part where
Like this? Okay.
and you can pull the other board up.
Maybe that's a good idea. Okay, so now you can see, right? This is better, but of course I have to do like this, but but it's okay. So now these are the objects, and let's say that we have a finite number of parameters, because in practice this u bar is described by some y, which is a finite dimensional space. So you have some u bar of y, and instead of LP you have some capital Y here. Okay, so this is the finite number of parameters that describe, in computation you always have to have finite number of parameters. For instance, by truncating a Gaussian random field. So you have objects like this that we can approximate. So this can be approximated by one more level of resolution, which is the integral of y of 0 to t. This is a d of psi of xt of g of u delta, right, of x t y. This is your numerical solution, because I put everything in terms of a delta. Then you have dx dt d mu bar of y, and this guy here I call it as my functional. I'll use it later. I call it as L, okay, L of y, L delta of y, because it's an approximation. So for instance, this L delta is an observable, right, because this is what I also showed you earlier. You can compute it on a given mesh. So what you're going to do in a multi-level method is that you're going to average this, or you're going to sample it in the following manner. So L, maybe the notation is unclear, but so I'm interested in this approximation, right? So I call this as L bar ml is an approximation to 1 over m0 summation of I from 1 to m0. I'll explain it. Let me just write it down. L delta 0 yi plus, now this is this famous multi-level formula, L from 1 to capital L 1 over m little l summation I from 1 to ml of L delta little l yi minus, oh, you can switch it off. Okay, that is good. Let me write it down and then we can explain this. And this is what is called a detail, DL. Okay, so the idea is the following. So you have a sequence of grids, right? So you have a sequence of grids. You have a coarse grid, then you have a finer grid, and then you have a finest grid. Let's say just 3 of these, something like this. So you have a sequence of grids. Now what you're doing is, so you have this observable, just for simplicity you could do this for a field. You have this observable. What you're doing is that you're sampling this observable on a coarse grid, on this grid, and you have a lot of samples on the coarse grid. Now on each of the finer grids, you take the same sample on 2 different grids, on 2 nested grids, for instance this and this, and compute the difference. For those who have seen wavelets, these are what are called details. They are also called details in this picture. So the same sample is evaluated on 2 grids, and the difference between these 2 is computed, and this is the formula. Okay, so it tells you, so this is essentially a telescopic sum. So this telescopic sum tells you that you can compute this mean here, which is given here, in terms of this formula here. So you have a sequence of grids. On the coarsest grid, you just compute the function, and then you compute the differences between the coarse and fine grids, and you do it iteratively. So this is multi-level. This is a very powerful, it is like thousands of citations these days, right, Håkon? Or 10,000 citations, or it's a very simple thing, but it is very powerful way of expressing. And why does it work? Now can I switch on the projector? Yes, or
the remote pressing the 1.
Remote with the 1, okay. AV mode, oh perfect. This was, okay, so now we can, okay, sorry. Okay, so the idea is, so this is a very complicated way to describe this simple thing. The bottom line on the coarse grid, oh, where is my clicker? On the coarse grid, you sample the function itself or the observable that is computed on the coarse grid, and between the coarse and the next coarse you compute this detail, between this and this you compute another detail, and you add this up. Okay? So this is sort of a combination formula it's called, and it's very powerful. My plan was to show why this converges, but given that we don't even have enough blackboards here, I'll just avoid it. And I'll just focus on, now I used a different, instead of L, I forgot that I've used capital G here. But essentially this is the same sort of formula. Just think of this, okay, you had a L there, you think of it as a G. Then we know that one can prove, this is many ways of doing that, but everything depends on these details, okay, because the whole thing is, so now this is the work done by MLMC, this is the multi-level Monte Carlo method, this is the work done by MC, L is the number of levels that you have, V0 is the variance of this guy here, okay, so this is not hard to prove this, okay, variance of this guy here, and VL is the variance of this guy here, okay, so this is the variance of this guy here, and I am assuming that there is some dyadic hierarchy in the grids, but other cases are also possible to work out. So now you can imagine that, look at some of the numbers here, roughly speaking. So speed up means this work done by this guy should be much less than the work done by Monte Carlo. There are two terms here. So of course for the first guy, V0, the variance of the coarsest grid is comparable to the variance of the underlying function as you can see. So this is order 1. This is L squared, which is bad because L is a big number, but we have 2 to the power LD plus 1. So this is exponentially small. So this will be a small term. The magic is here, right? So if these guys are of order 1, then they sum up to 1 and you don't get a speed up. You actually get a worsening of the estimate. However, if these guys decay, now these details are the difference between a coarse and a fine grid. So if the simulation converges, then the difference between a coarse and a fine grid is smaller and smaller and smaller. And if this decay, in particular if this decay with any sort of reasonable rate, then you get some sort of an exponential speed up. Okay? So everything now depends or relies on the decay of these variances. So you cannot predict for scalar conservation laws, you can prove that this decay is happening and it's quick, but for other problems it depends on a case by case basis. Let me give you some examples. Here's an interesting example, statistical solutions, so you can do that. Burger's equation, the simplest equation imaginable, but essentially white noise. So the initial data is white noise, just to do a difficult example, right? White noise means it's sort of, okay, formally, it's fractional Brownian motion with a so this is how it looks like. It really looks like noise, but because of the nonlinear evolution, you can see that it is averaged out, and once it is averaged out, you can see some shocks being formed and some nicer structure being there. So again, this fits the theory, it's still L2 valued, so it's square integrable, and these are the structure functions, they converge very nicely as before. This is Brownian motion and this is for essentially white noise, and this is the comparison between Monte Carlo, which was before. This is a function of work versus error. So now work is given in terms of the CPU time, I think. Yeah, I think it was CPU time. So you can see Monte Carlo has this decay, which is 0.23, not surprising here, but MLMC has a much better decay rate, and both for 0.5 and 0.01, and you get a significant speed up, right? So for instance here, let me give you an example. Already here you have 2 orders of magnitude speed up, right? So it starts here, and so this is almost 2 orders of magnitude speed up for the mean value. So for scalar conservation laws, it works, and you can prove that it works because these details, they become smaller and smaller and smaller. For systems, you have to check it on a case by case basis. So here's an example. So this is a nice interesting example. So this is a shock vortex interaction. So here is a vortex, this moves out here, hits the shock, and then there is some structure here. Some uncertainty, I think there are 11 uncertain parameters here, and this is how the mean value looks like. And this picture tells you, what does it tell you? So this is the decay of this is the actual variance, so the underlying variance, it converges to some quantity. This is the decay of the details, the difference between successive grids, the variance between them, it decays very nicely. and in red is the speed up. So you start getting a speed up depending on how many levels you take, but you get a factor of 10 speed up in this particular case, and this is consistent with the decay, but you can't prove it, right? You have to do the computation and find it. But what about Kelvin Helmholtz? Now this is sort of, you can't expect a lot here. Remember that each time we refined, we got more and more structure. So of course the difference between two resolutions is not really going to converge, and it doesn't. And in fact this is the picture that you get. So this is the variance which converges to something order of 1 quantity, but this is the variance of the detail, the quantity that has to decay. It doesn't really decay, it sort of remains constant. So as a consequence there is no speed up. MLMC is as good as Monte Carlo, so it didn't really work, except that there was one factor that we are missing. All these observables, there is a time averaging. The theory is for this was without any time averaging, but once you do some time averaging and look at observables at a time averaged, then indeed for both the first and the second moment you see some decay, and as a consequence you see some speed up. The speed up is not order of 10, but it is like 3 to 4, which is something, right? Remember that we needed a factor of 10, and if you get a factor of 5 you are happy with it. So with time averages you do have speed ups, and this makes you think that what if you take very long time averages, right? And this is exactly what we do in aerodynamics, where we compute the lift and the drag for steady state computations, which you can think of as long time averages. So this is a flow past two different aerofoils, NACA 0012, RA 2826, and this is there is a difference in the flow samples. This is the sort of mean the body forces, the CP values, and you can see the standard deviation, the mean plus the standard deviation for the two different aerofoils. And here MLMC really works, because this is the lift and the drag in both cases, and you can see, for instance, the detail, the variance is here, the decay of the detail is here, and you can see that there is a significant decay, and it's much smaller than the underlying variance. So in these cases you do get this sort of an exponential speed up. So in some problems multi-level Monte Carlo gives you 2 orders of magnitude speed up, some problems it gives you an order of magnitude speed up. In many problems which are more and more chaotic, it doesn't give you any speed up. So it's not a solution, but it's still something to be done, because it provides you with answers in many cases. Okay, so this was first attempt to do this. I'll be happy if there are some questions about multi-level. Yes?
Can you explain the time averaging again?
Why time averaging, or why does it
Why does it work? Because so if you get
time average quantities are better behaved. It's as simple as that. Okay, in fact I don't have a picture here on my laptop, but maybe it is there on my laptop. I can show you the same simulation that I showed you at a fixed time. I show the same picture time averaged, and you'll see that it is more regular. So time averaging reduces the variance of the chaotic behavior of the solution. That's the reason why it roughly works. And in practice you want time averages, right? The theory also tells you that it's only valid for time averages, but of course you can make them smaller and smaller. So smaller the time average, for no time averaging you didn't get any speed up. If you make small time averages, you get more speed up. This is order of 1 time averaging, then you get more speed up. So it's sort of, there is a play of factor here. Okay, so this is the reason why time averaging works. Further questions? Yes, awesome.
Directly related to MLMC, but I'm seeing that in a lot of these simulations, when you go from 512 to 1024, suddenly the rate changes. It becomes
because now you're hitting some asymptotic. Because in the sort of smaller grades, you really don't see anything practically, right? So you need some basic resolution. So once you start hitting there, you start getting some of the asymptotic behavior that you expect. So that could be one reason. Because we are always taking successive differences. It's not like we are taking a reference solution and comparing with the reference solution. Then that would explain that. No, we're taking successive differences. You get convergence so the difference between 512 and 1024 is not much. So there are 2 factors for it. Either the solution has converged, or you have a very slow rate of convergence. You cannot distinguish between both. In either case you can't do anymore. If it's a very slow rate of convergence, then you can't go to 10,000 cubed, right? Okay, so another option which is possible is to use what is called, and this will be relevant, I just quickly do it, is called quasi Monte Carlo. So quasi Monte Carlo, let me explain it a little bit, why it's important. So Monte Carlo is you just randomly choose points, right? Quasi Monte Carlo on the other hand, you choose them in a more smarter manner. So that this is a good example. If you look at, for instance, Monte Carlo random points, these are the blue points on a square, and you can see that there are many small squares on the grid where you don't see a single blue point. What Quasi Monte Carlo does is that it uses what is called a low discrepancy sequence. So you choose points which are not random, they are more deterministic, they are better distributed. It has what is called the equidistribution property. So you start getting points more and more places while still not suffering from the curse of dimensionality. So at least for, of course, if you take the midpoint of each grid, you are very well distributed, but then you suffer from the curse of dimensionality, because as you increase the dimensions, the choice of these points becomes sort of, there are too few points, right? Whereas with Quasi Monte Carlo, it's sort of a compromise between the two. And under certain smoothness assumptions, you can actually prove that there is some, this is approximation, this is a Wasserstein metric, this is approximation, and there is a decay which is actually faster than half, because Monte Carlo would do it at half, with Quasi Monte Carlo you will do better than half. But again, who tells you that that smoothness is there, right? In some cases it is there, and someone asked me this question about observables, that if you do lift and drag, for instance, you see the rate at which it converges, the Quasi Monte Carlo approximation, is 0.8. Why 0.8? I don't have a theorem about it. It's just observed that somehow there is more regularity to the lift and drag than to the field. And actually one of your colleagues this morning told me that he saw that, but this is an example of that. It's still significantly faster than Monte Carlo. So in this case, you can use Quasi Monte Carlo and it gives you good answers, right? On the other hand, Kelvin Helmholtz, it didn't. You see, so in Kelvin Helmholtz you have, so these are two different Quasi Monte Carlo methods, Sobol or points, Sobol and Halton. Monte Carlo was in orange, and these guys were in, you really don't get a speed up, right? I don't know, this is a speed up of 10% maybe. So it depends, Quasi Monte Carlo works in many cases, but there is no reason why it would work in all cases. So it's still a factor of 5 missing, I would say, or 3 to 4 that is missing. So the last part of the lecture, and this is, this again I repeat what I had said. So we need to compute statistical quantities, which are these observables, and in fact we need to compute the distribution of these statistical quantities. So this is what is called the push forward measure. So this is the distribution of this L under the underlying distribution, right? So this is just a marginal distribution for this quantity, okay? And as I said, with Monte Carlo you have this slow rate, and these are some of the issues, you know, the 3D costs, but already for this simple problem, flow past a transonic aerofoil, of course on a very fine grid, it's still 7 hours on a cluster. Okay, this is a second order finite volume method. It's a second. So the last method that I'm going to talk about will be a machine learning strategy. So this was contained in this particular paper, and I will stop after this. So machine learning these days, everything is about AI, right? So we are in the age of AI, whether it comes to translation, facial recognition, self-driving cars, or protein folding. Machine learning or deep neural networks are very important. They do these things. They can also be used in this context, and let me explain to you very briefly how. Okay, so the idea behind a neural network is very simple. It's just a composition of elementary functions. So this is a graphical representation. Input is typically a vector, output is a vector or a scalar, and you push the input to output through a sequence of layers, what are called hidden layers, and in each layer you do two things. You have a linear operation. So this is a linear operation, which is this matrix here, wk is a matrix, yk is the input to the layer, and this is a vector. So these are the weights and the biases, and then you have a pointwise application of a non. So you do a linear operation, which for instance connects all these guys together, and then you have pointwise nonlinearity. So within this you have pointwise nonlinearity, and this is what is called the activation function. For instance, the ReLU function. So you can think of a neural network, all of you should know this, otherwise you won't get a job when you graduate. So, so this is just a composition of simple functions. But it turns out that because it is composition, you can express functions, right? Because it's a composition, you can prove theorems, there is universality. Every function can be approximated by neural networks. What they don't tell you is how to do it. right? So this is how you do it. It's called supervised learning, the framework that I'm using. So you have, remember that I have a y, which is somewhere sitting here. For instance, your initial parameters or your boundary parameters. So this is your y, and what you're interested is in this map, the observable, or the field for that matter, which is your L delta of y, right? So this is a mapping between y and L delta of y. Uncertainty quantification is doing statistics of this. So now you have, so what you're going to do is you need data. So this is, you need some data. So you need some points yi for which you know the answer, for instance by a numerical simulation. And then you want a neural network which is able to approximate this function. So neural network is these elementary functions, and the difference between them for the data points is what gives you a loss function. So you want to minimize this. So the tunable parameters are the weights and the biases, right? So these are your tuning parameters, and you minimize that. You have some optimization problem, for instance, typically a stochastic gradient method, and then this gives you a trained neural network. So neural networks are elementary functions, you need data, and once you have data, you have a loss function. There's a stochastic gradient method which is going to give you the best fit with respect to the trained data. Now, how does the uncertainty quantification algorithm work with respect to this, right? So uncertainty quantification algorithm is very simple, because all that you are interested is in computing a push forward measure. You want the distribution of this L. So what you're going to do is you start choosing a training set. So y is your set of parameters, finite dimensional, could be very large dimensional, like this 962 dimension set that I showed you, and you choose some training points. This come from the distribution, for instance IID. For this, you evaluate the L delta, the map. This is the CFT or the PDE solver, right? You have the PDE solver, some integration routine. This gives you this. Then you do the training. It gives you the neural network. And now you have the neural network. You use that in terms of this push forward measure. So you compute all the statistics, not in terms of your original function, which you don't have access to except at a few points, but in terms of this neural network, which potentially you can have at large number of points. Okay, so this is what UQ in this context is, that you have the function and you can evaluate it multiple times, hopefully quickly, so you can use the Monte Carlo method on the neural network rather than on the function. Okay, so replace the function in your Monte Carlo routine with the neural network, but of course we need to train the neural network. For that you need to generate some data, for instance using a Monte Carlo method by IID samples. So this will be a two-step process. First, select the data points, train your network, and then do all the statistics by using the trained network. This is the basic algorithm here. Any questions so far on this? Yes?
So the network over the function values are evaluated at the grid points, let's say, and if I want to predict the function for a given.
But this is what I told you, right? For this presentation, this can also be done, because then it will just be a function of the grid point. But here I am interested in an observable. And what is an observable? Observable is you integrate over the grid points, right? So you integrate, this is the observable, so you integrate over the grid points. So choose a y, then calculate this L of y, which is this integral here, and this gives you a data point. Okay? So this is just for, but you can also do it over grid points. You'll see what is the difference of using a field and an observable. Yes, Håkon?
The training points yi, they're not the same as the yk.
No. They have to be independent, right? So otherwise, no. But for some methods that I'm going to show you, you can reuse, but not in a Monte Carlo context, because this should be independent. Okay, so the analysis of this algorithm was analyzed in this paper. So what we said is that this is the marginal distribution with respect to the observable. This is the one that we learn from the neural network. There is a metric between them, which is the natural Wasserstein metric. This scales as what is called the generalization error of your neural network. What is the generalization error? You have an underlying function, you have the neural network, and you compute the difference between them over the entire population. Okay, so this is the theorem. It's not very surprising. So if you want to speed up over Monte Carlo, you need several factors, sufficient conditions. First, you need this quantity to be small, because you want the difference between them to be small. So you need this quantity to be small. But to ensure that this is small, you should not take all the time generating the training set, so you need few training samples. Because if you have a lot of training samples, you can as well use Monte Carlo. Why should you do a neural network? So you need few training samples, and this is the key. And second, the cost of evaluating the neural network should be significantly less than the cost of numerical scheme. Because if the neural network takes as much time to evaluate as a numerical scheme, why don't you use a numerical scheme? So what many times people doing neural networks in scientific computing don't tell you are these things. They use 100,000 samples to train the network, and then do some application, but this, at least for uncertainty quantification, this doesn't work. Okay, so these things have to be guaranteed, and this is hard. Why is this hard? Because this is a theorem which can be proved. This was in this particular paper, which said that the generalization error in the L1 norm, but it could be in any norm. This is what we are interested in making small, right? This scales as a training error. The training error is what you compute, right? When you train, you can compute the training error. Plus, it can be estimated, what is called a generalization gap, can be estimated in terms of several quantities. This is the number of training points. This is Monte Carlo essentially. And this is the sort of variance that is there, which can be estimated in terms of the variance of the underlying function and the variance of the neural network. But let's say that these quantities are order 1. The main point is this 1 over square root of n. So for instance, to get 1%, assuming that your training error is 0, which is not true, but assuming a very low training error, even to get a 1% error requires 10,000 training samples. And then we are out here because we needed a few training samples, right? So we can't use that. And this is, in a way, the main challenge of, at least in my opinion, of using neural networks or deep learning, machine learning for scientific computing. Because then if you look at image recognition, there are tons of data that is available, right? But for scientific computing, we don't have a ton of data that is available, right? Because if you want to spread, of course, you have a lot of data available of an aircraft and what is the speed of the aircraft, but this is only in one regime. Whereas you need some statistical spread, then you have to do numerical simulations, which are expensive. So we don't have the sort of data that a computer scientist has for doing speech recognition or image recognition and so on. So the challenge is always learning maps, which are complicated. So I've said it's low regularity in sort of a relatively data poor regime. And you need some innovation. Directly this doesn't work. And in fact, this is a good bound because here's an example where we check this bound. So this is just a simple projectile motion. You throw a ball under drag and you see how far the ball goes. Okay, so here is the sort of error envelope or uncertainty envelope, and this is the training error. The training error is rather small with the number of training samples. This is our bound, and this is the generalization error. The generalization error is better than the bound, but at least the bound doesn't do such a bad job of calculating this. So this is a good bound. The bound itself is not problematic. So now we needed several ideas in order to do this. We have to learn the neural network or teach the neural network with a few samples. The first idea is, why should we use random points? Right? There's no reason why we should use random points. Certainly for moderate dimensions, we can use low discrepancy sequences. Remember that there's quasi-Monte Carlo methods. So these are low discrepancy sequences. There's a paper which analyzes this very carefully, which says that, okay, as long as your function has this bounded Hardy-Krause variation, some quantity, some variation, then this error scales like, okay, there is a logarithmic factor here, but for low dimensions you can ignore it. So it essentially scales like 1 over n, whereas this guy scales like 1 over square root of n. So you certainly get a benefit by just choosing different sets of data points. We decide, right? We are doing the simulations. So we decide which data points to take. So we can take this low discrepancy sequences. And this was a key idea. Then we remember that we are always computing observables. And observables have lower variance than the fields. Because fields are sort of observables, you have some averaging. So because of that, the sigma for an observable is smaller than that of a field. So we are on good grounds there. And this is an empirical fact, means there is no theorem, but this is an empirical fact. So we always try to learn observables. And we also do a more systematic training over the hyperparameters. You'll see as a result what happens. So here's an example. So there are a bunch of hyperparameters, number of hidden layers, number of units in each layer, different forms of the loss function, different initial guesses, and so on and so forth. There's a whole we want to learn the distribution over this set. So the example that we have is a flow past a transform. We have many examples, but the one I present is a flow past an airfoil here. So these are two different samples. You change the angle of attack, you change the shape, 6 uncertain dimensions, and this is the numerical solution is done with a higher resolution scheme. We have 128 Sobol points as the training set, which is a reasonable set here, and this is our architecture. So we have an input layer, 6 parameters, right? So this is 6 inputs, and these are 9 hidden layers. It's not very sensitive to this. This was just one choice, and the number of parameters that we have are 1149 parameters. So this is fully connected multi-layer perceptron, and this is the distribution of the error over all the parameters that we tested. Because this is more important. People generally tell you one parameter, this is the best parameter, but as you can see, this whole distribution does, okay, there are some outliers that we can forget. So this is the lift, and you can see that already with this network we get errors. A lot of these networks resulted in an error of less than 1 to 2% in the lift, okay, which is very satisfactory with 128 points. With the drag it was harder, but still many of them were around 5%. There's some real outliers that you can rule out, but this shows that with no luck, just by doing this process, you can get low errors for the lift and the drag. And the best performing network, so this is how the training proceeds. So you start with something, you do stochastic gradients, there's a lot of stochasticity, and then for both the lift and the drag, you saw that there was a reduction of the error by some orders of magnitude, and this was the prediction. So this is the actual data, the ground truth for the lift, and this is for the drag, and you can see that the more along the diagonal it is, the better the prediction you make, and you can see that it's really concentrated along the diagonal. With 128 points, this is a good prediction, and this is the relevant one, right? So for one of these good performing networks, for the lift you got an error of less than 1%, for the drag you got an error for less than 2%, and the point is in the cost, because to generate a single sample it is 7 hours, right? Remember that this was 7 hours CFD simulation. To train the networks, it took only 10 to 15 minutes, and to evaluate this one observable is 10 to the power minus 5 seconds, and in particular we have low errors. So all the conditions in the theorem that I had, where is the theorem now? It's here somewhere, right? Yeah, oh no, here. So we have low generalization error with a few training samples and at a significantly low cost of evaluation. So these theorems are satisfied, or these conditions are satisfied. So hopefully the UQ will look quite well. But as I said, the key was the choice of Sobol points, because if I did not choose Sobol points and if I chose random points, then you got at least a factor of 10 larger errors. So it really was, yes.
Where do you train your network?
This was just on a CPU. These are small networks.
CPU.
Yeah.
I noticed that you have 10 to the power 5.
Yeah. 10 to the power 5 seconds.
No, can you show the training?
Training, yes. Epochs, yes. This is 500,000 epochs, but this is a full batch.
Epochs, it's full batch?
Full batch, but only 128 samples, right? 128 samples.
128 samples.
It's a very small network.
It's rather big actually, because you have 9 hidden layers.
No, but it's 11. Yes, there is not no GPUs whatsoever. We can do it on. I think the exact machine is also said in the paper. I don't remember now, but this is really a CPU based. It's 500,000 epochs, but as you see that we already get the right loss function with I don't know 1,000 epochs. It's just we keep on pushing it because we didn't want to stop. But this is I can tell you the hardware. It didn't take long. The network is it is 9 hidden layers, but it has only 10 neurons per layer. You still think it's a large network with 1149 parameters? And this is done with full batch stochastic gradient descent, so it's not. This was 700. You see the exact numbers, right? Okay, 15 minutes. But the key is this choice of the Sobol points, because otherwise, in this particular case, and we have done many examples where this really led to a better choice. And you can see that you can see this when you change this is the mean of the networks, also the maximum and the minimum value. But look at the middle point here for the lift and the drag. So this is the mean error with respect to this hyperparameters for the number of training samples. So of course, as you have more training samples, you have a decay, but the decay is better than what is predicted by Monte Carlo. It's more consistent with what is predicted by quasi Monte Carlo, and this is the reason why it works. So more points, you get better predictions, that is, and you have a significantly faster rate of decay than Monte Carlo. What about UQ? Now you can learn the full measure. So this is the PDF of the lift, this is the PDF of the drag. The ground truth is a quasi Monte Carlo method with 1000 samples, and this is with 128 samples, the machine learning method, and you can see that they match quite well. The errors are small, and you get a speed up, the way we measured, of about 9 for the drag over quasi Monte Carlo and about 7 for the lift, but with Monte Carlo it is almost 200 in both cases. Quasi Monte Carlo already is a very good algorithm, so that's the reason why you, but still a factor of 9 you will take, and this is a genuine, we took into account the fact that we have trained and the training time and everything is taken into account, so it's a genuine thing, and this is very interesting because this tells you why UQ works. So this is a speed up, mean speed up, but maximum speed up. Mean speed up is more modest, but the maximum speed up over number of training samples. So you can see that the best answers that you have are when you have like 64 or 128 samples, because if you have more samples you get a better prediction, but your Monte Carlo method or quasi Monte Carlo method is more accurate. So to beat it you really need less number of samples, which is what it does. There is another idea which does it even better, which I have just explained to you, multi-level training. So there is no reason why my training should be based on one level of resolution. Why not use multi-level training algorithm? And this was done in this paper. And multi-level training, it's very easy to explain, just learn the details instead of the function itself. And here the speed ups in terms of prediction error are there significant. So it can be 5, 2 for instance for the lift, and for the drag it is about a factor of 5 to 6. And when you do UQ, this is over the machine learning algorithm, machine learning, multi-level machine learning, you have a factor of 5 to 6. And this is the final graph that I have, and after that we stop. So this is the lift and the drag. What we are computing is the Wasserstein distance of the PDFs, and these are 4 different methods. First one here is quasi Monte Carlo, which is quite good. Monte Carlo would be somewhere over here. This is the runtime, this is the error. So, and this is quasi Monte Carlo, multi-level quasi Monte Carlo, machine learning algorithm, multi-level machine learning algorithm. So you can see that multi-level machine learning algorithm is the winner, and machine learning itself beats quasi Monte Carlo quite a bit. So you get a factor of 10 to 20 when it does work. Anyway, so with that I stop. My whole point was that the uncertainty quantification for hyperbolic systems of conservation laws is hard because of the chaotic dynamics in particular, but also low regularity and high dimensionality. And I wanted to explain to you is statistical solutions are an appropriate framework. We have a very good theory for it. Particularly we have a convergent Monte Carlo algorithm. There are alternatives. You can use multi-level Monte Carlo, quasi Monte Carlo, deep learning. They work in many regimes. There are regimes where they still don't work. The other alternatives, stochastic Galerkin, stochastic collocation. I'm very skeptical about these methods for these problems because we don't have, they need some regularity, and we don't have the sort of regularity that is necessary. So I think I stop here first because I'm very tired. It has been a long day, and I'll be very happy if you have questions or if you need some references. All the material that I presented today is in papers which are either published or out on archives, so you can easily look it up. Okay, so ask me questions if you have, or if you don't have is also fine. No questions, huh? Or we are saturated with yes, Okon, you.
So in this statistical solutions, you have to treat the spatial point correlation, but you don't have to treat temporal.
No, that would be very bad, right? Because then temporal correlations means somehow you know into the future. So you want to evolve it. You don't want to.
But for SDs, you somehow have it in the past. I mean, you
Yes.
have some stability, I guess.
We have some time continuity. So we have some time continuity in the sense that in some negative, we have some continuity in time with respect to some negative Sobolev spaces. But there is some time no, we want to evolve, no? You don't want to know.
But it is because of the entropy correlation.
Yes,
More
that
spatial derivatives.
we have some weak control on the spatial derivatives. So that gives you some weak control on the time derivative, which is enough to have time continuity. So I don't want to do temporal correlation, but recover it as an emergent property, right? Because if you evolve it, then as a function of time, you have some regularity in some very weak Sobolev spaces for space, right? Yes.
Well, if there are no further questions, we'll conclude this session. And thank you very much for coming here. I think this was a very comprehensive.
Yeah. Thank you for attending.
Yeah, you considered different levels of knowledge of all the audience. Thank you very much.
Yeah.